the thought is almost too large to hold in the mind at once. A single interstellar object sliding silently through our solar system was enough to stir both awe and unease. But what happens when we stop treating it as an isolated event and start seeing it as the beginning of something far larger? The first interstellar visitor we ever confirmed, a strange elongated body named Oumuamua in 2017, seemed like a statistical accident at the time. Then came Borisov in 2019, a clear comet that burned with chemical traces from another star. And now Atlas, faster, stranger and older still, racing through the inner system with a carbon dioxide signature no one expected. 3 events across less than a single human lifetime. It forces a question we're no longer able to ignore. What if the trickle is the start of a flood? What if 3I Atlas is only the first of many? The certainty of science tells us not to panic. Celestial mechanics, orbital solutions, chemical spectra. The data are clear. These are natural objects, remnants of planet formation around distant suns, ejected by gravity and left to wander the galaxy for billions of years. They pose no danger to Earth. Their flyby distance is measured not in thousands, but in hundreds of millions of kilometers. Yet scientific reassurance collides with another instinct that refuses to stay quiet. If we keep seeing them, if our instruments keep catching wanderers that were once invisible, how long before the comfort of statistics gives way to something that feels more deliberate? It's here, in this tension between calm certainty and creeping paranoia, that the story begins. Astronomy tells us these objects are expected. Galactic models predict trillions of such bodies drifting between stars. Most are too faint for our current telescopes to see, but the more sensitive our surveys become, the more of them will appear in our sky. And yet, while mathematics frames them as background noise, human imagination fills the void with unease. What if the arrivals aren't as random as we believe? What if their chemistry, their trajectories, even their timing hide patterns we've been too cautious to name? The night sky has always been a mirror of human psychology. When something new crosses it, the temptation to read intention into the unknown is almost irresistible. For thousands of years, comets were treated as omens, messengers of catastrophe, heralds of war or famine. Science eventually stripped them of those roles, reducing them to frozen rock and dust orbiting the sun. Now with interstellar wanderers, we're back at the beginning of that cycle. Our tools tell us these are natural, but our imaginations whisper that the arrival of one after another could mean something else entirely. The worst-case scenario shifts from impact events or gravitational disruption to something more subtle, more disquieting. What if each new arrival is not just a visitor but a signal? This is where the speculation takes hold. Consider the sequence. Oumuamua slides past quietly, moving too fast for any spacecraft to reach it. Borisov follows, brighter, more obviously a comet, but still arriving and leaving before we can do much more than watch. Then Atlas, with its chemistry so extreme it defies explanation, forcing astronomers to propose theories that strain the edges of plausibility. The line connecting them is short but sharp. If 3 can arrive in such a small window of time, how many more are passing unobserved, and how many more will appear once the next generation of telescopes, like the Vera Rubin Observatory, begin their wide-field surveys? Predictions suggest we may detect several every single year once the instruments are fully operational. That means not just the occasional interstellar visitor, but a constant stream, a rolling presence of alien material sweeping through our neighbourhood. The shift is profound. We move from isolated anomalies to a background of arrivals, and with that shift, speculation multiplies. If these are random, they tell us about the formation of planets around other stars, about chemistry written in distant nurseries billions of years ago. But if they are not random, if frequency itself becomes the signal, then the implications stretch far beyond astronomy. They raise questions about intention, about surveillance, even about contact. Suddenly the possibility emerges that the galaxy is not silent at all, but communicating through objects so ancient and disguised that we mistake them for chance debris. This line of thought is not born of conspiracy or panic, but of the same curiosity that drives every scientific discovery. The difference is that it admits the unknown may be more than just statistical surprise. For every careful explanation grounded in chemistry and orbital mechanics, there exists a shadow version where each arrival hints at something larger. Natural models say these visitors are the scattered leftovers of planet formation. The speculative mirror suggests they could be reconnaissance, a census of developing civilizations, or even seeds of something we cannot yet define. The tension between these two frames of thought is not easy to resolve, and perhaps it never will be. When Atlas was discovered, astronomers moved quickly to reassure the public that it posed no threat. Its closest approach would be nearly twice the distance between Earth and Mars, more than safe. But buried in those reassurances is a truth that is both comforting and unsettling. These objects can appear at any time from any direction, travelling at speeds that render interception nearly impossible. We only see them because our technology has become sensitive enough to catch them. Before 2017, they had always been invisible. Now, in less than a decade, we have 3. The line between absence and abundance has blurred. The night sky, once considered empty of such visitors, may actually be crowded beyond imagination. This realization carries consequences that go beyond science. If wanderers are this common, then every planetary system in the galaxy is bleeding fragments into interstellar space. The void between stars is not empty but filled with travellers. Some are billions of years old, carrying within their cores the chemical fingerprints of long-vanished suns. Some may even hold the frozen building blocks of life scattered across the galaxy like seeds. And if life can travel this way, then so can the intentions of civilizations far older than ours. It is here that speculation and paranoia meet, blurring into scenarios where each new detection is not just a comet but potentially something designed. The opening question remains simple but heavy. What if Atlas is only the first of many? The answer begins with mathematics, shifts into philosophy, and eventually drifts into the realm of existential dread. Because when the sky becomes filled with wanderers, the challenge is no longer proving they exist. The challenge becomes understanding what their presence means. Are they silent fragments of ancient creation? Or are they messages written in chemistry, speed, and trajectory, waiting for us to notice? The story we tell ourselves about them may matter as much as the reality, because the human mind struggles to see repetition without searching for meaning. The first visitor was never the last. The pattern is already here. And as more arrive, the balance between certainty and paranoia will only sharpen. We know enough to feel safe, yet not enough to dismiss the possibility that safety is only an illusion. The story now moves into the shadows cast by probability, into the growing sense that our place in the galaxy is about to be redefined not by one object, but by the many that follow. When astronomers first pointed their instruments toward the faint streak of Atlas crossing the sky, they weren't only seeing light from a distant object, they were seeing the limits of their own tools reflected back at them. Every telescope, no matter how advanced, is a filter. It collects light, passes it, stretches it into spectra, and translates the raw hum of the universe into patterns human minds can work with. But filters do more than reveal. They also obscure. Between the photons that reach us and the conclusions we draw lies an abyss of interpretation, and within that abyss the shadows live. 3 interstellar visitors in less than 10 years should, statistically speaking, not have surprised anyone. Models of planetary formation long suggested the galaxy ought to be filled with such debris. The ejection of ice and rock during the chaotic birth of planetary systems is a violent process, scattering untold trillions of fragments into interstellar space. Yet when Oumuamua appeared in 2017, it shocked the world because none had been seen before. The surprise wasn't because they were rare, but because our instruments had been blind to them until the very moment one strayed close enough to notice. That blindness wasn't just technical, it was conceptual. For centuries, astronomy treated the spaces between stars as empty, clean, and silent. Now we know that silence was an illusion. But even knowing this, the question of what we are missing remains sharper than ever. Every detection carries with it a margin of error, a fuzz around the truth. Atlas is no exception. Its orbit is hyperbolic, its chemistry unusual, its speed extreme. All of those are measurable, but they're measured through layers of inference. A faint glow in a detector becomes a data point. A cluster of such points becomes a curve. The curve is fit to equations describing celestial motion. A spectrum is drawn from the light and bent through models of molecular absorption. Each step adds confidence but also risk. The shadows in the data live in those spaces where interpretation can bend in more than one direction. When scientists say Atlas is natural, they are speaking with the full weight of evidence. The coma it sheds is consistent with sublimating ices. The emission patterns align with known molecules. The trajectory fits cleanly within gravitational expectations. And yet, when examined closely, the numbers don't fit perfectly. The carbon dioxide concentration is extreme, well beyond typical cometary ranges. The absence of significant water signatures at large distances is puzzling. These are anomalies, and anomalies are the breeding grounds of speculation. They're also, historically, where the most important discoveries often hide. Pulsars began as inexplicable radio pulses. Quasars looked like stars until their redshifts proved otherwise. Cosmic microwave background radiation was first dismissed as interference from pigeon droppings in a radio antenna. Shadows in the data can be dismissed or embraced, but they rarely vanish quietly. For every astronomer calmly noting that unusual chemistry can be explained by natural processes, there is another voice wondering whether the anomalies are not signs of randomness but of design. The human brain, evolved to detect patterns in rustling grass and starry skies alike, struggles with the idea of pure coincidence. If Atlas is one data point, perhaps anomaly is expected. If Atlas is part of a growing trend, anomaly begins to look like signal. The shadows are not only in the light curves and spectra, but in our interpretation of what counts as meaningful. The tools we use also shape the shadows we see. Ground-based observatories struggle against atmospheric distortion, turning pinpoint light into smeared images. Space telescopes avoid that problem but face limitations of time, field of view, and sensitivity. No single instrument captures the whole truth. Hubble sees visible and ultraviolet light. James Webb peers into the infrared. Radio telescopes scan long wavelengths. Each produces a piece of the puzzle, but no piece alone explains the whole. When Atlas was analysed, Webb's data suggested high carbon dioxide dominance, while other instruments found more conventional signals. The overlap was partial, leaving gaps where interpretation became guesswork. Those gaps are where speculation creeps in. In public communication, scientists are careful. They emphasise certainty, because certainty reassures. NASA and ESA repeat that Atlas poses no danger, that its path is well understood, that its chemistry, while odd, is not impossible. But in the internal conversations of astronomy, the tone is different. There, questions are sharper. Why this much carbon dioxide? Why this velocity? Why this frequency of detections when theory said we should see so few? Professional caution prevents these questions from reaching headlines, but the questions remain. The shadows are as much cultural as they are scientific, shaped by the pressure to maintain authority and avoid feeding panic. This gap between public certainty and professional curiosity matters, because it's in that space that paranoia finds room to grow. When official statements emphasize safety and natural explanations, some assume that anomalies are being hidden. Conspiracies thrive in the shadows not because evidence supports them, but because uncertainty invites imagination. Atlas is a case study in how data that appear mundane to experts can spiral into exotic speculation outside professional circles. When the numbers don't fit perfectly, the stories multiply. Some speak of alien probes disguised as comets, others of surveillance disguised as random trajectories. Most of these ideas collapse under scrutiny, but scrutiny itself rarely travels as far or as fast as speculation. The real challenge lies not in proving what Atlas is, but in proving what it is not. Evidence of natural processes is abundant, but absence of artificial signals does not prove absence of intent. Radio telescopes detected no coherent transmissions, but perhaps none were sent. Trajectory analysis showed no controlled maneuvers, but perhaps none were needed. Thermal profiles aligned with solar heating, but perhaps any active systems are shielded. In this way, shadows persist. No matter how thorough the analysis, the possibility of what we cannot detect always remains. That is the paradox of interstellar visitors. They can be studied only briefly, at immense distances, and then they vanish forever. Each becomes both a solved mystery and an eternal question mark. Looking back at Oumuamua, the same dynamic is visible. Its unusual shape and slight non-gravitational acceleration were eventually explained as consistent with natural outgassing and tumbling. But for some, those explanations felt stretched. For others, they felt like closure. The shadows in that data remain, even as the object races away into interstellar night, never to be studied again. Borisov was more straightforward, a textbook comet. Atlas is both comet-like and anomalous, a mixture of certainty and mystery. The pattern is not one of clear resolution, but of recurring questions. Each new visitor adds to the pile of data, but also deepens the sense that the shadows will never disappear entirely. This leads to the larger concern. If Atlas is only the first of many, then the shadows in the data will only multiply. Every detection will bring anomalies. Some will be chemical, others orbital, others observational. Individually, each may be explainable. Collectively, they may point towards something we don't yet recognize. It is one thing to dismiss a single comet's strange chemistry. It is another to dismiss a dozen such cases across different arrivals. Patterns only emerge through repetition, and repetition is exactly what the future promises. The next generation of surveys will deepen this process. The Vera Rubin Observatory, with its ability to scan the entire southern sky every few nights, will flood astronomy with detections. Predictions suggest several interstellar visitors per year will soon enter the catalogue. Each will be studied, each will display quirks, each will cast shadows of uncertainty. The scientific value is immense. Glimpses into planetary systems beyond our own, chemical diversity on galactic scales, histories older than our solar system. But alongside the value lies the inevitable. Speculation will grow in proportion to the anomalies. The more shadows we find, the more people will ask what they are hiding. This is the pivot point where science and paranoia meet. Shadows in the data are not flaws, they are opportunities. But they also invite interpretations that escape the control of evidence. In that sense, the greatest challenge of future interstellar detections may not be technical but psychological. How will we, as a species, handle the flood of uncertainty that comes with each new object? Will we learn to accept anomalies as part of nature's diversity, or will we see them as coded signals, as signs of surveillance, as harbingers of intentions not our own? Atlas is not just a comet, it is a rehearsal. The way we interpret its shadows will shape how we interpret the many that follow. Already, debates ripple through conferences and research papers. Some push for more aggressive searches for artificial signals. Others warn against fueling speculation. Some argue that even considering the possibility of design undermines public trust in science. Others counter that avoiding such questions blinds us to possibilities we cannot afford to ignore. The shadows demand attention, but attention itself changes the story. The truth is that shadows in the data will always remain. No instrument is perfect, no measurement free of error, no interpretation immune to bias. Atlas, like its predecessors, embodies that truth. It is at once a clear comet and a question mark, a visitor from the galactic dark that reveals as much about our own limitations as it does about itself. And as we prepare for the many that will follow, we are forced to confront not only the mysteries of the objects themselves, but the shadows in our own methods, our own minds, our own need to find meaning in patterns that may or may not exist. The journey continues not with the next object alone, but with the recognition that every observation is also an invitation to confront uncertainty. Each detection is a reminder that our instruments are powerful but imperfect, our interpretations grounded but fragile, and in that fragile space between light collected and meaning assigned, the shadows will always wait. By the time astronomers confirmed Atlas as the third interstellar visitor, the framing had already shifted. One could no longer point to a single discovery and call it an anomaly. The silence of centuries had been broken not once, but repeatedly, in quick succession. First, Oumuamua in 2017, then Borisov in 2019, and now Atlas in 2025. 3 data points may not constitute a trend in strict statistical language, but they are more than enough to redefine expectations. Where once the idea of an interstellar wanderer entering our solar system seemed remarkable, it now seems almost inevitable. The real question is not how extraordinary these 3 were, but how many others passed unnoticed before our instruments were capable of seeing them. It's worth remembering that Oumuamua was discovered almost by accident. A routine sky survey designed to spot near-Earth asteroids happened to catch a faint moving point that didn't fit the expected orbital shapes. Borisov, brighter and more obviously cometary, was noticed by an amateur astronomer using a modest telescope, highlighting that many of these visitors could have passed through without anyone realizing. Atlas, for its part, was spotted by a dedicated survey program, the kind designed precisely to scan the sky, night after night, for new objects. The pattern is clear. The only reason we now have 3 confirmed visitors is because our methods of watching the sky have improved. This raises an obvious conclusion. If our tools have only recently reached the sensitivity to detect such objects, then the 3 we've seen are not exceptional intruders, but representatives of a population that has always been there. That population must be immense. Models of planetary formation predict that every star system expels a vast number of icy and rocky fragments during its early evolution. The gravitational billiards of giant planets, stellar companions and passing stars throw debris outward, scattering it into interstellar space. Multiply that process by hundreds of billions of stars across the galaxy, and the number of wandering objects becomes unimaginable. What we've seen so far is only the faintest tip of an iceberg that extends through this galactic dark. This realization changes the scale of the problem. If trillions of interstellar objects are drifting between stars, then it is not surprising that some wander into our neighbourhood. In fact, it would be surprising if they didn't. What is unusual is not their existence, but that we have been blind to them for so long. Until recently, our telescopes lack the power to detect faint, fast-moving points against the backdrop of stars. Only with the advent of wide-field, automated surveys, combined with advanced algorithms capable of tracking unusual trajectories, has the floodgate opened. And if 3 have been found in less than a decade, then dozens, even hundreds, should be within reach in the coming years. Yet statistics alone are not enough to quiet the unease. For each new object, the temptation arises to ask whether its arrival is truly random. We tell ourselves they are scattered debris, but human perception is primed to interpret repetition as pattern. 3 confirmed visitors in such a short span feels like something more than chance, even if mathematics insists otherwise. That tension will only grow as detections multiply. When the 4th, the 5th, and the 10th are found, the story will no longer be about anomalies at all. It will be about the presence of countless unseen wanderers constantly sweeping through the solar system, most too faint to notice, but all silently passing through the skies above. Astronomy thrives on sample size. With only one interstellar visitor, every anomaly was amplified. Oumuamua's elongated shape and strange acceleration became mysteries debated worldwide. With two, Borisov's more conventional nature suggested diversity among wanderers. With three, Atlas's unusual chemistry sharpened the contrast. Once the numbers grow larger, patterns may emerge that resolve these questions, showing us the range of what is normal for such objects. But until then, each detection carries disproportionate weight. Each is treated as both a messenger and a mystery. And in that role, they embody more than science. They embody speculation about what lies beyond. It is here that the phrase countless unseen takes on meaning beyond statistics. If most interstellar wanderers remain invisible, then our picture of the galaxy is incomplete. Every confirmed visitor is not just an isolated object, but a reminder of the many we miss. This ignorance is not benign. Consider that some wanderers may be far larger than Atlas, with nuclei stretching tens of kilometers across. Others may move at even greater speeds, leaving only the faintest traces behind. Some could carry exotic chemistries that defy our understanding of planetary formation. Others might come close enough to Earth to raise questions about impact risk, even if probability remains low. By definition, we don't know what we're missing, and that ignorance is both humbling and unsettling. The unseen also invites another kind of speculation. If wanderers are truly countless, then it is statistically possible that a small fraction may not be natural at all. Even if 99.9% are fragments of ice and rock, the remaining fraction could represent something else entirely. A probe disguised as debris, a device engineered to survive across billions of years, or even just a relic of some civilization long since gone. The odds of encountering such an object are slim, but when the population is measured in trillions, slim odds still translate into real possibilities. Every unseen wanderer carries with it not just scientific data, but the possibility, however faint, of something profoundly different. This is the heart of the unease. We can model populations, calculate detection rates, and predict future discoveries with confidence. But the possibility of encountering something outside the models will never disappear. The unseen hides both the mundane and the extraordinary, and until each object is observed, we cannot know which it will be. The shadows in the data, already troubling, grow deeper when multiplied by countless unseen companions. What makes this situation unique is its inevitability. Unlike other cosmic mysteries that require extraordinary conditions or rare alignments, the arrival of interstellar objects is guaranteed. They are not rare fireworks, but constant background noise. We are not waiting for improbable events. We are waiting for the continuation of a process that has been happening all along. The only change is our awareness, and awareness changes everything. The idea of countless unseen wanderers reframes our relationship with the galaxy. No longer can we think of our solar system as isolated, a self-contained system drifting quietly through the void. Instead, it becomes part of a traffic flow, a node along routes traced by debris billions of years old. These visitors are not occasional intruders, but constant reminders that our neighbourhood is porous, that material from distant stars passes through without invitation, without notice. The interstellar medium is not empty. It is a vast ocean of fragments, and we are only beginning to glimpse the waves. In this ocean, the three confirmed visitors are like ships sighted from shore. Each is a hint of larger traffic patterns beyond our vision. We may never know how many passed unseen in the centuries before telescopes. We may never know how many pass unseen even now. But we do know that as our instruments sharpen, the number of confirmed sightings will rise. And with each new arrival, the tension between statistical certainty and speculative unease will deepen, because every new object confirms the vastness of the unseen, and every anomaly hints at meanings beyond the natural. The challenge for astronomy is balancing these two truths. On one hand, the population of unseen wanderers is a scientific treasure. Each offers a sample of alien geology, a fragment of chemical history from a different star. Together they can map the diversity of planetary formation across the galaxy. On the other hand, the same population is a breeding ground for speculation, because every detection comes filtered through incomplete data. Each object vanishes into the dark before we can study it fully, leaving questions unresolved and suspicions untested. The countless unseen may carry more answers than we can ever extract, and in that gap between what we know and what we can imagine, speculation thrives. What emerges is a picture both reassuring and disquieting. Reassuring because the flood of interstellar visitors proves we are not isolated. Material from across the galaxy flows through our system, carrying knowledge we can study. Disquieting because each new detection reminds us of the many more we will never see, and of the possibilities that may be hidden within them. The balance between science and speculation, certainty and paranoia, will only sharpen as the numbers rise. And rise they will, because the three confirmed are not the story. The story is the countless unseen, waiting in the dark, moving silently across the galaxy, slipping past our instruments until the moment one of them appears and forces us once again to ask what it means. When astronomers confront the scale of interstellar wanderers, numbers quickly lose their ability to shock. It begins with simple probability. A single planetary system like ours produces countless fragments of ice and rock in its formative years. Most are consumed, colliding with planets, moons, or the star itself. But a fraction are flung outward, accelerated by gravitational encounters until their orbits exceed escape velocity. They drift away, carrying with them the fingerprints of their origins, and once freed, they never return. Multiply that process by hundreds of billions of stars in the galaxy, and the result is staggering. The galaxy should not merely contain interstellar wanderers, it should be overflowing with them. The discovery of 3 confirmed visitors so quickly after the start of systematic surveys aligns perfectly with this prediction. Far from being outliers, they are early representatives of a population that must number in the trillions. Oumuamua, Borisov, and Atlas are not unique jewels stumbled upon by accident. They are the first drops from a downpour that has been falling for billions of years. The statistics demand it. The probability of our solar system avoiding such encounters for eons is vanishingly small. The only reason it seemed so until now is because we were blind. Our instruments lack the precision to see the faint lights racing across the sky, so we assume the sky was empty. Once the mathematics are laid bare, the illusion of rarity collapses. Researchers model the expected density of interstellar objects by working backward from the detections we already have. If 3 have been spotted in less than a decade of surveys, the implied number drifting through the galaxy at any given moment must be astronomical. For everyone large enough and close enough to be noticed, there may be millions more too faint to see. Some estimates suggest that at any moment, tens of thousands of such wanderers are passing within the orbit of Neptune. Most are no larger than boulders, far too small for current telescopes, but they are there nonetheless, silent and invisible. This statistical certainty reframes the story of Atlas. Its chemistry may be unusual, its velocity extreme, but what matters most is that its detection confirms a larger truth. Interstellar objects are not rare visitors. They are constant companions. The solar system is not an isolated bubble floating in a sterile void. It is a crossroad on galactic highways trafficked by debris older than our sun. And once the traffic is acknowledged, the next step is inevitable. We must ask not only how many there are, but what stories they carry. Probability suggests that among trillions of wanderers, diversity must be immense. Some will be icy comets like Borisov, their surfaces still rich with volatile compounds. Others will be dry and rocky like Oumuamua, their ice is long since burned away. Some will be enormous, dwarfing any comet yet catalogued, while others will be dust-sized fragments scattered invisibly through space. Chemistry will vary with stellar environment, reflecting the abundance of carbon, oxygen, nitrogen and metals present when each system formed. Some will carry water, others exotic ices like methane or ammonia, and still others may contain compounds unknown to Earth. With numbers this vast, the range of possibilities is limited only by what physics allows. Statistics also imply something else, less comfortable but unavoidable. The more visitors arrive, the greater the chance that some will not fit neatly into natural categories. Outliers are inevitable. With a large enough sample, anomalies accumulate, and anomalies are where speculation flourishes. A comet that behaves too predictably, a rock whose trajectory hints at subtle control, or an object whose chemistry appears engineered rather than formed. Any one of these would ignite debates far beyond astronomy. The odds of such anomalies increase not because design is likely, but because vast numbers guarantee strangeness. Probability ensures not only normality but exceptions, and exceptions fuel paranoia as much as discovery. This is why the statistics of the infinite unsettle as much as they reassure. On one hand, they make interstellar visitors ordinary. They explain why we should expect many more detections in the near future. On the other, they open the door to scenarios that cannot be dismissed with a simple wave of the hand. When the sample is infinite in practice, every possibility, however small, becomes inevitable somewhere. The question becomes whether we will recognize it when it passes through our sky. The mathematics extend beyond population counts. They touch on timescales. Each wanderer has travelled for millions or billions of years before arriving here. That journey means they sample environments across the galaxy, carrying information from regions we may never reach. When a fragment from a distant system enters our telescopes, it represents not just another data point, but a messenger from a different time and place. Multiply that by the vast number of wanderers, and the implication is profound. The galaxy has been conducting a slow-motion exchange of material for as long as it has existed. Every star contributes to it, and every system, including ours, is part of the flow. From a scientific standpoint, this circulation is a gift. Each object that passes through our solar system is a natural probe, offering us a chance to study alien chemistry without leaving home. By collecting spectra, tracking trajectories and analysing light curves, we build a catalogue of planetary processes across the galaxy. In time, statistics will allow us to see patterns, how common water-rich comets are, how rare carbon-dominated ones might be, what stellar populations produce certain chemical signatures. The infinite becomes a laboratory, with each wanderer a sample in an experiment billions of years in progress. Yet the same logic that delights scientists unsettles the imagination. If trillions of wanderers drift between stars, then our skies are part of a galactic network of messengers. And once framed that way, the question shifts. If nature uses these wanderers to exchange material, might intelligence also use them? A civilization older than ours by millions of years would not need to build elaborate spacecraft to send probes across the galaxy. It could hide them among the countless natural fragments, indistinguishable, except to those who know what to look for. Statistics guarantee that among the infinite, concealment is trivial. Every rock becomes camouflage, every comet a potential disguise. The plausibility of such scenarios is secondary to the realization that the numbers allow them. With a background population so vast, intention can vanish into randomness. That is both reassuring and disturbing. It means that if we never find evidence of design, the statistics still hold. If we ever do, it will be almost impossible to prove it wasn't chance. The infinite makes every conclusion provisional, every certainty fragile. This fragility is not unique to astronomy. Statistics in medicine, in economics, in climate science all carry the same duality. They provide confidence while leaving space for exceptions. But in astronomy, the stakes feel different. The infinite is not just a model. It is the scale of the universe itself, indifferent to our need for clarity. Interstellar wanderers embody that indifference. Each one is ordinary when seen in statistical context, yet extraordinary when it passes close enough to notice. The infinite reduces them to inevitabilities, but our experience of them remains singular. That tension will never go away. The lesson from statistics is clear. More are coming. Not a handful, but a stream. Once the Vera Rubin Observatory begins its surveys, astronomers expect to catalogue interstellar objects at rates approaching several per year. Some predict even higher. The infinite will become tangible, filling databases with orbits, magnitudes, and spectra. Each detection will be another confirmation of the galactic background, but also another opportunity for anomaly. And every anomaly will test our ability to separate science from speculation. The real challenge may not be in the numbers themselves, but in what they reveal about our psychology. Humans are not naturally equipped to think in statistical terms. We respond to the dramatic, the singular, the anomalous. 3 confirmed visitors in less than a decade feels like a signal, even though mathematics says it is expected. 10 or 20 more will reinforce the reality of abundance, but anomalies among them will dominate attention. The statistics of the infinite will reassure scientists, but they will also fuel public paranoia, because the infinite does not erase the possibility of the extraordinary. It multiplies it. The story of Atlas is inseparable from this context. Its detection is not just about a single comet, but about what its existence says about the population as a whole. Its unusual chemistry could be an outlier, or it could be part of a broader category we have yet to define. Only by adding more detections can we know. Until then, Atlas embodies both the certainty of statistics and the unease of exceptions. It is one thread in an infinite tapestry, visible only briefly before disappearing forever. The infinite ensures there will be others, but it also ensures that uncertainty will remain. As more objects appear, the statistics will harden into confidence. The density of interstellar wanderers will be better constrained, the range of chemistries mapped, the diversity of shapes catalogued. But no amount of statistics will erase the shadows entirely. The infinite guarantees not just normality, but strangeness. And it is in that strangeness that the speculation will always live. The more often interstellar visitors appear, the harder it becomes to treat them as isolated curiosities. At first, each seemed like a self-contained story. Oumuamua appeared, startled astronomers, and vanished into the dark before its secrets could be resolved. Borisov followed, behaving more like a comet, with its long tail and chemical markers making sense within natural expectations. Then Atlas arrived, an object that combined the cometry with the unexpected, carrying carbon dioxide levels that stood out in ways no one anticipated. Individually, these stories can be contained, but together they suggest something more. Patterns begin to emerge, not only in the objects themselves, but in the way we respond to them. The Wanderers are more than rocks and ice. They are mirrors reflecting both the galaxy's history and our own shifting understanding. The first pattern is frequency. Before 2017, the number of confirmed interstellar visitors was 0. In less than a decade, there are now 3. If one looks forward rather than backward, models suggest the pattern is accelerating. With advanced surveys coming online, it will not be 3 in 10 years, but dozens within the same span. Frequency turns anomalies into statistics. Each new detection makes the next one feel less remarkable, and yet the sense of strangeness doesn't disappear. Instead, it moves. It shifts from the fact of their presence to the details of their behaviour. Once frequency is accepted as normal, attention focuses on chemistry, trajectory, and structure, searching for the deeper stories hidden within the data. Chemistry provides one of the strongest hints of pattern. Borisov resembled comets from our own system, but with subtle differences in the abundance of certain compounds. Its spectrum suggested origins in a cold, volatile-rich environment, likely far from the star that formed it. Atlas, by contrast, displayed carbon dioxide in concentrations far above what models predicted. That detail suggests an entirely different formation history, possibly within a system where carbon dominated over oxygen or where water ice was depleted early. Oumuamua, frustratingly faint, left chemistry unresolved, but its lack of a visible coma was itself a clue. If seen together, these three suggest that interstellar wanderers carry fingerprints of their home systems in their volatile content. Patterns in chemistry become patterns in origin, mapping the diversity of planetary nurseries across the galaxy. Trajectory offers another layer. All three confirmed visitors shared hyperbolic orbits, proof they came from beyond the sun's gravitational influence. But even within that category, differences matter. Oumuamua's entry direction traced back toward the relative motion of nearby stars, suggesting it came from the general galactic field rather than any specific system. Borisov's velocity was high, but still within the range expected of ejected comets. Atlas moved faster still, raising questions about whether it had been accelerated by encounters with multiple stars, or even by interactions within a dense stellar nursery. The pattern here is not of identical motion, but of shared origin in chaos. Wanderers arrive not from one place, but from everywhere, their paths shaped by billions of years of galactic interactions. Shape and structure add yet another dimension. Oumuamua's elongated form, whether cigar-like or pancake-flat, became one of its defining mysteries. Borisov looked like a conventional comet, round nucleus, diffuse coma, long tail. Atlas, though faint, suggested fragmentation, possibly breaking apart as it approached the sun. At first glance, these forms seem unconnected, but together they sketch a pattern of variety. The diversity of shapes is itself meaningful, reflecting the different stresses, collisions and erosions these objects endure during their journeys. Patterns emerge not in uniformity, but in diversity, showing that interstellar space is a crucible of transformation. Each wanderer is both representative of its origin and sculpted by its travels. But patterns are not only physical, they exist in our reactions as well. The public response to Oumuamua was astonishment and speculation. Its odd trajectory and acceleration led some to wonder aloud about artificial origins. With Borisov, attention shifted to relief. It looked like what astronomers expected, a natural comet, reassuring in its familiarity. Atlas reignited curiosity, its strange chemistry opening new questions. This sequence reveals a pattern in psychology. The first arrival shocked us. The second soothed us. The third unsettled us again. The next may follow this cycle or break it entirely, depending on what anomalies it presents. The wanderers don't just reveal patterns in themselves, they reveal patterns in us, in how we balance wonder, fear, and the need for explanation. One might ask whether these patterns are real or illusions of small numbers. 3 objects are hardly a sufficient sample to draw firm conclusions, yet the human mind cannot resist finding structure even where randomness rules. This is both a strength and a weakness. It allows us to generate hypotheses, to treat chemistry and trajectory as clues worth following, but it also tempts us into seeing intentional design where none exists. The idea that wanderers might arrive in a deliberate sequence, each carrying hidden messages, grows naturally from the human tendency to impose order. Whether the universe is offering patterns or we're inventing them is a question without an easy answer. From a scientific standpoint, patterns are tools. By cataloguing chemistry, trajectories and shapes across dozens or hundreds of interstellar objects, we will eventually distinguish randomness from meaningful distribution. If Atlas's carbon dioxide dominance turns out to be common, then it signals a frequent type of planetary chemistry in the galaxy. If it remains unique, then it is an anomaly to be explained. The same logic applies to speed, structure, and every other measurable property. Over time, the patterns will clarify, transforming speculation into knowledge. Until then, every detection hovers between the two. Each wanderer is both data and enigma, a single dot in a picture not yet complete. Yet even when patterns become clearer, the possibility of hidden layers will remain. The galaxy is vast and our instruments limited. What we see will always be filtered through technology and interpretation. That means patterns may emerge that are artifacts of our methods, rather than truths of the objects themselves. Selection bias, detection thresholds, and observational gaps all shape the data. What appears to be a cluster may be a mirage. What looks like a sequence may be coincidence. The Wanderers teach us not only about the galaxy, but about the limits of our own perception. Still, the temptation to search for deeper meaning will not vanish. The idea that Wanderers might serve as messengers, either of natural processes or of something more intentional, lingers at the edge of every anomaly. Patterns in chemistry might one day hint at panspermia, the transfer of life between systems. Patterns in trajectory might suggest clustering around certain regions of the galaxy. Patterns in frequency might reveal epochs of increased arrivals linked to galactic dynamics. Each possibility carries implications that stretch beyond science into philosophy. The Wanderers are not only physical objects but questions written across the sky, and patterns are the language we try to read them in. Looking at the three we have, the most honest conclusion is that patterns exist but remain incomplete. We see hints of diversity in chemistry, differences in speed, contrasts in shape. We see repetition in hyperbolic trajectories and in the inevitability of arrival. We see cycles in human reaction. None of these is enough to declare certainty, yet none can be ignored. The Wanderers demand attention because they embody the intersection of randomness and structure. They remind us that patterns are not only things we find, but things we create, shaping our interpretation of the universe around us. And as more arrive, the patterns will deepen. Some will confirm expectations, others will challenge them. Together they will form a picture, not of a single narrative, but of a galaxy in motion, scattering fragments across the void. Each object is a sentence in a story billions of years long. Each detection is a chance to read a line of that story, incomplete but suggestive. The Wanderers are not accidents. They are part of the fabric of the galaxy, and the patterns they carry are part of the fabric of us, as we try to understand our place within it. Among all the qualities that make interstellar visitors remarkable, none is more striking than their speed. To astronomers, velocity is not just a number, it is a fingerprint. It tells the story of where an object has been, what forces have acted upon it, and whether its origins lie within our solar system or far beyond. When we speak of Oumuamua, Borisov and Atlas, their shared distinction is not merely that they came from outside, but that they moved so quickly that the sun's gravity could never hold them. Speed is what marked them as foreign. Speed is the proof that they are wanderers from the galactic sea. For ordinary comets, speed is predictable. They are bound to the sun, travelling on elliptical orbits that repeat over years or centuries. Their velocities rise as they approach perihelion, the point of closest approach, then slow as they recede, but always within the range defined by gravity's grip. With interstellar visitors, the numbers break that mould. Oumuamua entered the solar system at over 26 kilometers per second relative to the Sun, already faster than any bound object should be. After swinging past, it accelerated slightly, likely from outgassing, but even without that push, it was clear it would never return. Borisov followed at nearly 33 kilometers per second, another hyperbolic escapee. Atlas arrived moving faster still, its speed so high that astronomers traced its path back through interstellar space without finding a plausible nearby origin. Speed, then, is not incidental, it is the defining trait. Without it, these objects would be indistinguishable from long-period comets drawn from the distant Oort cloud. Their hyperbolic velocities are what prove they belong to another star, ejected from their birth systems long ago. The sheer pace at which they move past us ensures that every encounter is fleeting. By the time telescopes detect them, they are already rushing away, allowing only weeks or months of observation before distance dims them beyond reach. The rapidity of their passage is as much a limitation as it is a revelation. We know they are here, but we never know them deeply. The significance of speed extends beyond mere classification. It speaks to the violence of their past. To fling a fragment of ice or rock into interstellar space requires immense gravitational interactions. In our own system, it is Jupiter that serves as the great ejector, slingshotting comets onto hyperbolic orbits when they wander too close. Other systems have their own giants, and some may have binary stars or chaotic clusters that hurl debris outward with even greater efficiency. The velocity of a visitor is a fossil of those ancient encounters. Oumuamua's moderate speed suggested a relatively ordinary ejection. Borisov's higher velocity hinted at a more energetic origin. Atlas, moving at extremes, may have been accelerated not once but multiple times, tossed from system to system like a stone skipping across galactic currents. If speed is a signature, then each visitor carries a different autograph. The numbers alone do not tell us which star they came from, but they do constrain the possibilities. A slow-moving interstellar comet might plausibly originate in the local stellar neighbourhood. A fast one, like Atlas, likely began its journey far away, shaped by complex interactions before it ever crossed our path. In this way, velocity becomes a map, sketching the hidden routes of migration across the galaxy. Each detection is a data point in a larger picture of how stars exchange material through gravitational scattering. The more visitors we track, the clearer the map will become. But speed carries with it another layer of meaning, one that invites speculation. In the absence of context, unusually high velocities can appear unnatural. When Oumuamua's acceleration was detected, even though it was slight, some proposed it could be the result of artificial propulsion. Later studies suggested natural explanations, but the fact remains that speed, especially when anomalous, draws suspicion. If a visitor arrived moving in ways inconsistent with known ejection processes, or if its trajectory hinted at subtle corrections rather than freefall, it would raise questions far beyond astronomy. Velocity, in such a case, would be not only a signature of origin, but a possible signature of intent. This is why astronomers scrutinize every measurement. A hyperbolic trajectory is expected, but any deviation from the curve defined by gravity alone demands explanation. In most cases, outgassing can account for the difference, as sublimating ices release jets that act like miniature thrusters. In Oumuamua's case, the lack of a visible coma made that explanation less satisfying, though it remained the most plausible. Atlas too displayed chemical signatures strong enough to justify non-gravitational forces, though its extreme speed, even without those effects, made it a special case. The line between natural variation and something more deliberate is razor thin, and speed is always the variable that draws attention to that line. Beyond speculation, velocity has practical implications. High-speed visitors pose no threat of capture. They cannot be pulled into bound orbits by the sun. This means they pass through and are gone, impossible to study up close with current technology. Spacecraft cannot be launched quickly enough to intercept them once detected. Even theoretical missions require years of preparation, making surprise arrivals nearly impossible to reach. If we are to study them directly, we will need pre-positioned spacecraft or entirely new propulsion systems capable of chasing targets moving at tens of kilometers per second. Until then, speed remains both their identifier and their shield. It marks them as interstellar, but it also denies us access. Velocity also frames the scale of interstellar travel. At 30 kilometers per second, a wanderer crosses the distance from Earth to the Moon in less than 4 hours. At that pace, it takes only months to move from the outer solar system to the inner planets. Yet even at such immense speeds, crossing the gulf between stars takes millions of years. Speed as we measure it in these visitors is breathtaking in local terms but glacial in galactic ones. Each object is ancient by the time it reaches us, carrying with it the record of eons. Their motion is fast enough to escape, but not fast enough to erase the weight of time. This paradox, to swift in our sky, slow in the galaxy, is part of their allure. To us, their passage is a brief spectacle, gone almost as soon as it is noticed. To the galaxy, they are drifting embers, moving leisurely across the void. Speed is relative, and relativity shapes our perception of significance. The Wanderers remind us that what feels urgent and fleeting on human timescales is part of a rhythm measured in millions of years. They are both sudden and eternal, fast and slow, depending on where one stands. Patterns in speed may prove as informative as patterns in chemistry. If most Wanderers arrive within a certain velocity range, it will tell us about the typical dynamics of ejection from stellar systems. Outliers may point to unusual processes, close encounters with massive stars, interactions in dense clusters, or gravitational slingshots across multiple systems. Some velocities may even suggest origins in regions of the galaxy with higher stellar density, such as the inner disk or near star-forming complexes. Each measurement is not just a number, but a clue about the galactic environment that produced it. And yet, no matter how carefully we analyse, speed retains its dual role as both fact and mystery. It tells us where an object does not belong, but rarely tells us where it came from. It reveals the violence of ejection, but not the details of the event. It marks an object as interstellar, but leaves the rest of its story hidden. In this way, speed is both signature and silence. It identifies, but it does not explain. It proves the Wanderer is alien, but leaves the question of purpose unanswered. As more objects arrive, velocity will become one of the first traits examined, a shorthand for classification. But it will also remain a source of unease. For every object that fits the statistical norm, there will be one that stretches it. For every curve explained by gravity, there will be a deviation demanding justification. And in those deviations, suspicion will grow. Speed will always be the first thing that sets these Wanderers apart, and so it will always carry the weight of meaning beyond what the numbers strictly allow. The story of interstellar visitors cannot be told without velocity at its core. It is the marker of their foreignness, the reason they are fleeting, the clue to their violent pasts, and the boundary that keeps us distant from them. It is also the variable that tempts us most to speculate, to imagine hidden propulsion, deliberate design, or signals encoded not in light but in motion. Whether seen as science or as speculation, speed is the signature we cannot ignore. It is written into every detection, every orbit, every fleeting passage across our sky. And as the number of Wanderers grows, it will be speed that first distinguishes the ordinary from the extraordinary, the natural from the possibly intentional, the expected from the unsettling. If speed is what tells us that interstellar visitors are foreign, then chemistry is what tells us what kind of foreigners they are. Every streak of light through a telescope, every faint signature pulled apart by a spectrograph, is more than just a line of data. It is the chemical autobiography of an object that has travelled farther than we can imagine. When astronomers speak of Atlas, they do not simply note its velocity or trajectory. They fixate on the strange imbalance of molecules in its coma. Because chemistry is where anomalies become undeniable. Chemistry is the place where patterns start to matter. For comets native to our solar system, chemical composition follows familiar rules. Water ice dominates, with carbon dioxide and carbon monoxide in smaller proportions. Other volatiles like methane, ammonia, and trace organics appear depending on distance from the Sun and the comet's age. Variability exists, but within expected ranges. When Borisov passed through in 2019, its spectrum showed similar compounds, albeit in slightly different ratios. That alone was remarkable, because it suggested that cometary chemistry is not unique to our solar system. Planetary systems light years apart may still produce similar frozen leftovers. In Borisov's case, the differences were subtle but informative, hinting at colder formation conditions than most of our comets experience. It was alien, but comfortably so. Atlas shifted that comfort. Observations showed unusually strong carbon dioxide signatures, levels far exceeding what models predict. At the same time, the water component, normally abundant in comets near the Sun, appeared diminished. The result was a chemistry that seemed inverted compared to expectations. Natural explanations exist. Perhaps Atlas formed in a disk where carbon-rich ices dominated, or perhaps water was lost long ago through thermal processes. But even when framed as natural, the anomaly remains striking. Why this much carbon dioxide? Why so little water? Why does this comet, unlike others, look chemically extreme? The question grows sharper when compared across the 3 confirmed visitors. Oumuamua, faint and comoless, offered no clear chemical data, only the absence of visible outgassing. Borisov resembled a standard comet, reassuring in its similarity to our own. Atlas tilted the balance back into strangeness with its carbon-dominated profile. If these 3 are representatives of a large population, then chemistry is not uniform. Diversity is expected, but the extent of it raises questions. Are we seeing a random sampling, or do these objects cluster into categories that reflect deeper galactic processes? If water-rich comets, carbon-dominated comets, and dry fragments all exist in abundance, what does that say about the environments in which they were born? Chemistry becomes more than science when anomalies stack. For centuries, comets in our own system were studied as time capsules, preserving the primordial conditions of the solar nebula. Interstellar comets expand that principle outward. Each one is a time capsule not of our history but of someone else's. In principle, they offer us glimpses of planetary systems we may never reach. But if their chemistry does not align with expectations, then they are more than samples. They are puzzles. Each chemical imbalance is a riddle, asking what processes shaped it, and whether those processes are natural or something else entirely. This is where speculation enters. Chemistry is not just about molecules but about intent, at least in the imagination. If an object carried compounds in proportions too specific to dismiss, some would see it as engineered. A comet dominated by unusual isotopes, for instance, would raise suspicions of artificial origin. A fragment carrying molecules rarely found in nature might be interpreted as a signal. Atlas does not reach that threshold, but it brushes against it, its carbon dioxide levels strange enough to provoke whispers. Even when science provides natural explanations, the fact that chemistry allows multiple interpretations leaves space for unease. The real value of chemistry lies in statistics. A single anomaly proves little, but dozens can reveal patterns. If future visitors show the same carbon-dominated chemistry as Atlas, then what now looks like an outlier will become a category. That category would suggest entire classes of planetary systems where carbon dioxide plays the role water does in ours. On the other hand, if Atlas remains unique, then it may point to rare or extreme conditions in its birthplace. Either result reshapes our understanding of galactic diversity. The galaxy may be filled with systems producing comets like ours, or it may be a patchwork of wildly different chemistries, each tied to the quirks of local environments. But chemistry is also fragile. Spectroscopic measurements are sensitive to distance, brightness, and interference. Misinterpretations are possible, and subtle errors can skew results. With interstellar visitors, the window for observation is short. By the time telescopes are trained on them, they are often already receding, their brightness fading. Atlas was observed with the James Webb Space Telescope and several ground-based instruments, but even so, its data were incomplete. Gaps remain where assumptions must fill the void. Those assumptions become part of the chemistry, shaping what we believe the object is made of, and in those gaps shadows remain. The question of chemistry is not only about the objects themselves, but about how we read them. When scientists emphasize water, carbon dioxide, or methane, they are choosing which features to highlight. Those choices influence public perception. A headline saying Atlas dominated by carbon dioxide suggests alien strangeness. A headline saying Atlas shows comet-like chemistry suggests normality. Both statements are true, but each frames the story differently. The chemistry does not change, but the way we tell it does. Patterns can be emphasized or minimized depending on what narrative we choose. Beyond science and speculation, chemistry carries practical implications. Some researchers suggest that interstellar objects may deliver prebiotic molecules across systems, acting as couriers of life's building blocks. If Atlas is carbon-rich, then perhaps it carried complex organics frozen within its core. If Borisov was water-rich, then it may have transported frozen oceans. If Oumuamua was dry, then it may have been a shard of a larger body already stripped of volatiles. Taken together, these objects illustrate multiple pathways by which material can move between stars. The chemistry they carry could seed worlds, shape atmospheres, or even influence the origin of life itself. In this way, the question of chemistry becomes a question of biology, yet the same logic invites darker speculation. If chemistry can seed life, then chemistry can also be manipulated. An engineered object could carry molecules designed to survive interstellar journeys, acting not as natural seeds, but as deliberate messengers. The statistical probability of such a scenario is low, but it cannot be dismissed outright. With trillions of wanderers, even a tiny fraction of artificial ones would still mean some exist. Chemistry would be the key to identifying them, the only clue left behind as they race silently past. And because chemistry is ambiguous, certainty may never be possible. As detections increase, the question of chemistry will dominate analysis. Each new visitor will be dissected spectroscopically, its molecules catalogued, its anomalies debated. Some will align with expectations, others will not. Over time, the distribution will clarify, but until then, every anomaly will invite speculation. Atlas is not just a comet. It is a reminder that chemistry can surprise us, that the universe is not obligated to match our models, and that every deviation from expectation feels like a whisper of something more. The Wanderers bring with them not just mass and motion, but stories written in molecules. Reading those stories requires caution, but also imagination. Chemistry is both proof and provocation. It proves that alien systems produce familiar compounds, but it also provokes questions when ratios deviate. In the end, the question of chemistry is not one that will ever fully close. Each object answers some questions and raises others, and the cycle repeats endlessly. What matters is not resolving every anomaly, but learning how to interpret them without falling into certainty or paranoia. Chemistry, like speed, is a signature, and signatures are always open to interpretation. Every interstellar visitor that cuts across our sky is not just a traveller from elsewhere, but a survivor of timescales that dwarf the history of our own world. The stone, ice, and dust that form these bodies have drifted in darkness longer than any civilization has existed, longer than Earth itself has been home to complex life, in some cases longer than our planet has even had incontinence. When astronomers talk about Oumuamua, Borisov, or Atlas, they are speaking not only of objects moving at high speeds, but of fragments carrying with them a memory of the galaxy that stretches back billions of years. They are ancient messengers, not in the sense of intent, but in the sense of endurance. Their very existence is a message about survival across cosmic time. To understand why this matters, one must look at how long these wanderers have been adrift. A fragment ejected from a young planetary system does not simply vanish into the void, it drifts. For millions or even billions of years it crosses interstellar distances at speeds that, while enormous by our standards, are glacial compared to the galaxy as a whole. At 30 kilometers per second, a visitor like Borisov could take millions of years to travel from one side of the local stellar neighbourhood to another. If its journey began farther away, near the galactic core or in a dense star-forming region, then it may have been travelling since before Earth formed. The ice in its core would predate the oceans, the crust of rock might predate our sun itself. In that sense, every interstellar comet is a messenger carrying material older than our entire system. This is not poetic exaggeration, but straightforward astrophysics. planetary systems form in disks of gas and dust around young stars. During those chaotic times, collisions and gravitational interactions eject vast numbers of objects into interstellar space. Some of these are destroyed quickly by stellar radiation or by colliding with other bodies, but those that survive the first few million years often persist indefinitely. Once ejected, they drift with nothing to stop them. There is no drag in space, no erosion except from rare cosmic rays, no collisions except with other unlikely wanderers. Survival becomes the default. Billions of years later, some of those survivors pass near us, and when they do, our telescopes record them as faint points of light. In reality, they are fragments of history, carriers of galactic memory. The chemistry of these objects underscores their role as messengers. The unusual carbon dioxide of Atlas, the water-rich ices of Borisov, the dry mystery of Oumuamua, each reflects the environment in which it formed. But more than that, each preserves information about a time and place we can never visit. The stars where these bodies began their journeys may no longer even exist. They may have burned out, collapsed into white dwarfs, or exploded as supernovae scattering heavier elements across space. The wanderer remains, drifting silently, carrying with it the last physical record of a vanished system. In this way, they are not just samples of other stars, they are relics of entire histories erased from everywhere else except within their cores. This framing reshapes how we interpret them. It is easy to view each detection as a present-tense event, an object now moving across our solar system. But the truth is that what we see now is only the most recent chapter in a story billions of years long. When Atlas was discovered, astronomers traced its trajectory back into the galactic field. But no origin star could be identified. That uncertainty is not a failure of calculation, but a reflection of reality. Stars move, shift, and drift around the galaxy over billions of years. The birthplace of Atlas may no longer be anywhere near the path we trace today. Its parent system could be long gone, its memory erased from everywhere but in the molecules frozen in Atlas's body. The comet itself becomes the archive, the silent witness to a history we cannot reconstruct otherwise. Seen in this way, the wanderers embody the galaxy's memory in physical form. Their distributed archives, scattered throughout the Milky Way, carrying within them chemical records of star formation, planetary processes, and environmental conditions from across cosmic time. They remind us that the galaxy is not static. It has a long memory, and that memory is written into fragments that drift endlessly until, by chance, they encounter systems like ours. When we analyse their light through spectrographs, we are not merely studying comets, we are reading from a library that spans the galaxy. Each line in the spectrum is a line of text, each molecule a word in a language of history. But memory is not always clear. Over time, radiation damages molecules. Cosmic rays split apart chemical bonds, surfaces erode. What remains when an object finally passes near a star may be a damaged, incomplete record. The deeper interiors may still preserve pristine material, but from Earth we only see the outer layers sublimating into comas and tails. The message is partial, fragmented, like a manuscript eaten away by centuries. We learn what we can, but the gaps are as telling as the signals. Every anomaly may be the scar of time as much as a reflection of origin. In this sense, interstellar chemistry is not only about what was present at birth, but about what survived the journey. The concept of wanderers as messengers also intersects with speculation. If natural fragments can preserve memory across billions of years, then in principle, so could artificial ones. A civilization seeking to leave a record might choose to encode it in durable fragments ejected into interstellar space. Such objects would drift indefinitely, outlasting stars waiting to be intercepted. This is not fantasy, but an extrapolation of the very property we already observe: longevity. The galaxy already uses interstellar debris as a library of memory. Whether intelligence might one day exploit the same mechanism is a question that lingers at the edge of astronomy. The fact that we cannot distinguish perfectly between natural anomalies and deliberate design only fuels that speculation. Even without invoking intelligence, the idea of memory challenges us. We often think of the galaxy as vast and empty, but the truth is that it is filled with relics. Every interstellar visitor is proof that the past is not gone but scattered. Our solar system is not an isolated present, but part of a continuum where ancient material from other systems crosses paths with us. The stones that fall into our skies may contain the memory of stars that burned before the sun was born. The comets that flare briefly in our telescopes may carry molecules older than life on Earth. When framed this way, every detection becomes more than science. It becomes a confrontation with time itself. Consider the philosophical weight of this. Humanity has always sought memory. From carvings on stone to digital archives, we struggle to preserve the past against decay. Yet here, in the cold dark between stars, memory persists without effort. The galaxy has been keeping its own record in the form of drifting debris, each fragment a messenger of an unremembered history. We are only now learning to read it. The question is not whether the galaxy remembers, but whether we are capable of interpreting what it has preserved. Every spectrum we collect, every chemical anomaly we debate, is an attempt to translate messages written long before we existed. In this translation, caution is necessary. Not every anomaly is profound. Some are noise, some are damage, some are the inevitable result of billions of years of exposure. Yet even noise is part of the story. Memory is never perfect, whether in human minds or galactic debris. What matters is recognizing that imperfection does not erase meaning. It complicates it. Atlas's strange carbon dioxide is not a pristine record, but a record nonetheless. Oumuamua's silence is itself a statement about the conditions of its survival. Borisov's similarity to our comets is a reminder that some processes are universal. The messengers speak in fragments, but fragments are enough to build stories. As detections multiply, the role of these objects as messengers will only grow clearer. Some will confirm our models, others will challenge them. Some will carry familiar molecules, others will surprise us with chemistries we have not imagined. Together they will expand the archive, filling in the library of galactic memory. But as the archive grows, so will the tension between science and speculation. For every researcher carefully piecing together chemical histories, there will be voices asking whether memory can be intentional, whether messages can be deliberate. The wanderers will always invite such questions, because their survival across billions of years makes them plausible carriers, not just of molecules, but of meaning. In the end, the truth may be simple. These objects are messengers not because they were designed to be, but because they endure. Their persistence across time is enough to make them carry memory, whether we read it or not. To stand under the night sky and know that a faint point of light represents a fragment older than Earth is to feel the weight of that memory. It is a reminder that the galaxy does not forget. Even when stars die and systems collapse, the debris remains, drifting until, by chance, it enters our vision. And when it does, we are confronted with a messenger we cannot ignore, carrying with it the history of a galaxy too vast to comprehend, yet written clearly in the chemistry and motion of a single wandering body. The first time an interstellar visitor was spotted, it was an astonishment. The second time, it was a validation. The third time, it was a confirmation that our solar system is not exempt from the flow of material drifting endlessly through the galaxy. But what happens when the count rises beyond 3, beyond 10, beyond what feels manageable to track or explain? What begins as wonder can slowly shift into unease, because frequency is not only about statistics. Frequency carries with it implications about patterns, and when patterns grow dense, they can start to feel like warnings. Astronomy thrives on the principle that more data brings more clarity. A single comet from another star is a puzzle. 2 comets suggest comparison. 3 suggest a spectrum of possibilities. Dozens promise a distribution that can reveal trends, helping scientists distinguish between the ordinary and the extraordinary. Yet human psychology does not always follow this logic. To scientists, more detections strengthen confidence in natural models. To the public, more detections can feel like escalation, as if something has changed in the cosmic order. When an event shifts from rare to routine, the meaning shifts with it, and that shift does not always soothe. Consider the timeline we already have. For centuries, no interstellar object was known. Then, within less than a decade, 3 appeared. Statistically, this is expected once surveys become sensitive enough, but expectation does little to calm the feeling that frequency is accelerating. With the Vera Rubin Observatory preparing to scan the sky with unprecedented precision, predictions suggest that interstellar objects may soon be detected every year, perhaps multiple times per year. Each will be catalogued, studied, and explained. But the very fact that detections become annual, even seasonal, transforms them from marvels into background noise, and in that background, paranoia can take root, because when something is no longer rare, it feels like it has purpose. The difference lies in framing. A single detection can be written off as luck. A handful can be written off as coincidence. But when the numbers grow into dozens or hundreds, it becomes increasingly difficult for the human mind to accept randomness as the only explanation. We are conditioned to interpret repetition as intent. It is a survival instinct, a way of detecting predators, prey, or allies in the natural world. That instinct does not vanish in the face of astrophysical data. It lingers, whispering that frequency is not just probability but message. This tension is already visible in discussions about Atlas. Some interpret its arrival after Oumuamua and Borisov as simple consequence of improved observation. Others note uneasily that 3 visitors in less than a decade feels like a pattern forming. If that unease exists now, with only 3, imagine the atmosphere when detections number in the double digits. The warning will not come from the objects themselves, but from the way we interpret their frequency. The danger is not physical, at least not immediately. It is psychological. Frequency changes perception, and perception changes meaning. But what if frequency does matter beyond perception? Astronomers insist that the expected background of interstellar wanderers is immense, and therefore frequent detections are inevitable. Yet even within that model, patterns can carry meaning. For instance, if multiple visitors arrive clustered in time, it could reflect real galactic dynamics, a stream of debris from a disrupted planetary system crossing our region of space, or a dense population of fragments from a nearby star-forming region. In this scenario, frequency is not just a matter of better telescopes, but of genuine cosmic clustering. That clustering could continue for centuries, altering the solar system's environment in subtle ways. If we are entering a stream of galactic debris, frequency itself is a message about our position in the galaxy. More unsettling still is the possibility that frequency could mask intent. Natural models explain frequent detections as statistical inevitability, but if arrivals ever align too neatly, if chemistry repeats in suspicious ways, or if trajectories hint at synchronization, then frequency would cross a line from comfort to alarm. At that point, it would be difficult to dismiss the possibility that what looks like debris is instead a survey, a census, or even reconnaissance. Again, the probabilities are low, but when numbers grow large, low probabilities no longer feel negligible. With trillions of wanderers in the galaxy, even rare scenarios are bound to occur somewhere. History shows how quickly frequency changes interpretation. When comets appeared sporadically in ancient skies, they were feared as singular omens. When they became more frequent in telescopic records, they were recognized as natural, predictable phenomena. The shift calmed fear but did not erase the instinct to assign meaning. Today, Interstellar wanderers are in the same transition. We are moving from astonishment to familiarity, but familiarity does not erase unease. Instead, it raises a new question. If they are so frequent, what larger story are we failing to see? From a scientific perspective, frequency is opportunity. Each detection adds to the data set, allowing researchers to test models of planetary formation, galactic dynamics, and chemical diversity. Over time, frequency becomes the foundation of knowledge, the proof that wanderers are not curiosities but fundamental parts of galactic evolution. Yet even within this framework, frequency carries warnings. The more objects we see, the more we realise how little control we have. We cannot intercept them, cannot predict them far in advance, cannot study them beyond brief windows. Their abundance is proof of our vulnerability. The solar system is open, porous, exposed to endless traffic we cannot regulate. Frequency reminds us not only of opportunity but of helplessness. This helplessness shapes the darker interpretations. When visitors are rare, they are safe to romanticize as anomalies. When they become frequent, they force us to confront our inability to monitor them all. If 10 interstellar objects pass through in a decade, we could not study each in detail. Most would slip by with minimal data. Each one of those could, in principle, carry more than natural chemistry, but we would never know. The warning embedded in frequency is not that danger is certain, but that ignorance is guaranteed. The flood of wanderers will overwhelm our ability to interpret them fully. That imbalance between presence and understanding is where fear grows. The transition point is not far away. Once Rubin begins operations, the number of detections is expected to surge. What was once extraordinary will become routine. Each object will be another point on a growing list, but the anomalies will stand out, and with them the suspicion that repetition is not just randomness. Frequency makes anomalies harder to ignore. One strange chemistry can be dismissed, 2 can be debated. But if 10 visitors in a row show unusual traits, coincidence begins to lose its grip. At that point, frequency itself becomes the warning, not because the objects intend harm, but because their behaviour resists explanation within the framework of chance. Even if the anomaly is proved natural, the perception will linger. Once frequency crosses into abundance, speculation is inevitable. Some will see it as a sign that the galaxy is more active than we imagined. Others will see it as surveillance, as if we are being observed systematically. The truth may remain firmly within astrophysics, but the interpretation will expand beyond it, shaped by culture, media, and fear. Warnings need not be intentional to feel real. They emerge from the human need to see meaning in repetition, and that need will only sharpen as the sky fills with wanderers. The wanderers do not need to change for their meaning to change. The shift comes from us. What was once a marvel becomes a pattern, and what was once a pattern becomes a warning. That progression is not driven by the objects themselves, but by their frequency. Each new arrival adds weight, pushing perception from chance toward intent, from comfort toward unease. The warning is not about collision or invasion, but about the realization that our place in the galaxy is more exposed, more observed, more entangled than we once believed. In the years ahead, frequency will test our balance between science and paranoia. Researchers will see a treasure trove of data, but the public may see a steady drumbeat of omens. Between those views lies the truth. Frequency is both. It is opportunity and it is warning. It tells us the galaxy is filled with fragments, and it tells us that fragments can never again be ignored. The more we detect, the more the pattern grows, and with each new point of light, the line between random and deliberate becomes harder to define. When Oumuamua was first detected, the immediate conclusion was that it was an accident of observation, the product of chance alignment between our telescopes and a stray visitor. When Borisov followed only 2 years later, the narrative shifted toward validation. This was proof that interstellar comets existed in abundance, and that the first was not an impossible fluke. With Atlas arriving in 2025, the conversation subtly shifted again. 3 detections in less than a decade began to stretch the comfort of coincidence. If wanderers are this common, then what we see may represent only a fraction of what actually passes through. And if what we see appears clustered in time, then the uneasy question surfaces: is this random, or is there something more deliberate at work? In science, coincidence is often unsatisfying but necessary. Randomness explains distributions, fluctuations, and clustering better than intention in most cases. Events happen near each other in time not because they are coordinated, but because statistics allow clusters. A lottery may produce 2 winners in the same town by accident, just as meteors may fall on 2 regions of Earth in short succession without design. But when those coincidences stack, when they feel too neat or too frequent, human psychology rebels against chance as an answer. That rebellion is not irrational. It is rooted in the survival instinct that tells us patterns matter. If danger lurks, it will announce itself through repetition, and when the sky itself begins to repeat, doubt creeps in. Astronomers insist that the clustering of 3 detections is no surprise. The expansion of survey capabilities explains it cleanly. Before 2017, our instruments were not sensitive enough to find small, fast-moving interstellar objects. Once surveys improved, a detection followed naturally. The coincidence is not in the sky, but in our progress. Yet this explanation, while scientifically satisfying, struggles against the broader perception. To those outside the discipline, the story feels different. Centuries of silence, followed by 3 visitors in less than 10 years, carries the weight of design, even if no evidence supports it. The conspiracy is not in the data, but in the interpretation. This gap between statistical coincidence and perceived conspiracy is where speculation takes root. If arrivals are not random, what could they mean? One scenario imagines reconnaissance. Each visitor a probe disguised as natural debris, timed to survey developing civilizations. Another imagines communication, with arrivals intended as messages delivered not by signals, but by physical presence. A third scenario imagines simple inevitability, that galactic processes release streams of objects at intervals, and we happen to be living through one of those intervals. Each explanation stretches the imagination differently, but all rest on the same unease. Coincidence feels inadequate when the universe appears to notice us. Even within science, coincidence is never the final word. When patterns emerge, they are tested. Are the arrival times of Oumuamua, Borisov, and Atlas consistent with random distribution, or do they suggest a stream of objects moving together? Some researchers have speculated about associations with stellar groups, suggesting that debris released from a disrupted system could produce multiple arrivals in clustered timeframes. If that is true, then the coincidence is not random, but the result of shared origin. That still counts as natural, but it reframes the story. What looks like conspiracy is instead the galaxy's own choreography, stars scattering fragments in waves rather than singly. Yet suspicion does not vanish with natural explanation. Conspiracies thrive not because they are supported by evidence, but because they exploit gaps in explanation. The timing of arrivals is one such gap. Why now, after centuries of silence? Why 3 so close together? Why chemistry that seems to shift from familiar to strange? Science says our instruments have improved. Conspiracy whispers that someone, somewhere, has chosen this moment. The danger is not that the conspiracy is true, but that it feels compelling in ways data cannot easily counter. The history of astronomy offers parallels. When pulsars were first detected, the regularity of their signals led some to nickname them LGM, short for little green men. The hypothesis of alien origin was discarded quickly once multiple examples were found, showing they were natural neutron stars. But for a moment, coincidence of discovery aligned with conspiracy of interpretation. The same dynamic is unfolding now with interstellar wanderers. The first one was shocking. The second was reassuring. The The third destabilized the narrative again. Until we have dozens, maybe hundreds, the balance between coincidence and conspiracy will remain fragile. It is also worth considering that coincidence and conspiracy are not mutually exclusive. Cosmic coincidences can coexist with human conspiracies. Even if the objects are natural, the way information about them is handled can feed suspicion. If data are delayed, if interpretations seem inconsistent, if official statements emphasize certainty while anomalies remain unexplained, conspiracy narratives grow. People begin to imagine not only that the arrivals are deliberate, but that agencies know more than they admit. The conspiracy becomes less about the objects themselves and more about the institutions studying them. The timing of discoveries feeds the suspicion, but the management of information sustains it. This interplay of coincidence and conspiracy matters because it shapes public trust. Science requires patience, careful observation, and acceptance of incomplete answers. Conspiracies thrive on immediacy, on filling gaps with narrative. When objects like Atlas appear, the data take months to analyse, but speculation spreads instantly. By the time careful papers are published, conspiracy theories have already cemented themselves in public imagination. The coincidence of clustered arrivals becomes a conspiracy of hidden meaning, regardless of what the data say. The warning here is not only about objects in the sky, but about our ability to interpret them responsibly. From a broader perspective, coincidence itself carries lessons. The galaxy is vast, and our place in it is not central. To expect arrivals to space themselves neatly across centuries is anthropocentric. The clustering of 3 visitors in less than a decade is remarkable to us, but on galactic timescales, it is nothing. Millions of years separate most events in the galaxy. A few clustered decades mean little in that context. Coincidence is the natural result of our narrow perspective, compressed into the timescale of human lives. What feels like conspiracy may simply be the universe reminding us that our sense of order is not universal. But the reverse possibility, however unlikely, cannot be dismissed outright. If frequency continues to rise and patterns emerge that resist natural explanation, the suspicion of conspiracy will sharpen. If objects arrive with trajectories too neatly aligned, or chemistries too systematically varied, or speeds too narrowly distributed, then the line between coincidence and conspiracy will blur further. At that point, the burden of proof will not only be on scientists to explain natural mechanisms, but on humanity to decide what to do if coincidence ever ceases to be convincing. Until then, we live in the ambiguity. Every new detection is another roll of the dice, another chance for coincidence to stretch into discomfort. The conspiracy is not in the sky, but in our minds, born of the unease that comes when randomness feels too heavy to accept. Whether the arrivals are truly random or part of larger patterns, the fact remains that our ability to distinguish between them is limited. The wanderers come, and we interpret them as best we can, balancing between the simplicity of coincidence and the seduction of conspiracy. The truth, for now, lies somewhere in the shadow between the two. There is a comfort in rarity. When something happens only once in a lifetime, it can be marvelled at, studied, even mythologized, without disturbing the foundations of how we see the world. Rarity is manageable. It lets us separate the extraordinary from the ordinary and reassure ourselves that what we witness is special but not threatening. The problem comes when rarity begins to fade, when extraordinary events happen often enough to stop feeling isolated. The human mind begins to search for new ways to categorize them. A single interstellar visitor was a marvel. A second was an affirmation. A third became a trend. What happens when there are 10? When there are 50? At what point does the threshold of too many push wonder into unease? For astronomers, the answer is quantitative. The more detections, the better. Each new interstellar object adds to the growing data set. allowing population models to be refined, chemistry to be compared, and galactic dynamics to be tested. To a scientist, there is no such thing as too many. Each visitor is a sample, a data point, a chance to learn more about how planetary systems across the galaxy form and evolve. But outside the discipline, abundance carries a different weight. Too many visitors too quickly feels less like a natural background and more like a build-up, as if something in the universe has shifted. That feeling, even without evidence, is powerful enough to reshape the narrative. The threshold of too many is not defined by a number alone, it is defined by perception. If detections remain occasional, once every few years, they remain in the realm of curiosity. If they accelerate to once or twice a year, they begin to feel routine. If surveys like the Vera Rubin Observatory reveal multiple new wanderers every year, the story changes again. Routine becomes saturation, and saturation forces reinterpretation. People begin to ask why now, why so often, why this clustering in our era? The scientific answer, that our technology has finally caught up to what was always there, is correct but unsatisfying. The psychological answer, that frequency signals meaning, is harder to dismiss. Part of the unease lies in visibility. Interstellar visitors have always existed, drifting through the solar system unnoticed. Their abundance is not new. What is new is our awareness. But awareness transforms experience. When we were blind, the sky felt empty. Now that we can see, the sky feels crowded. That crowding will only intensify as detections increase. To those tracking orbital catalogues, it will be proof of progress. To others, it will feel like encroachment. The sky, once infinite and serene, will be perceived as populated by endless foreign bodies arriving without pause. The threshold of too many is crossed not when the numbers grow large, but when the sense of intrusion becomes unavoidable. Even within science, the idea of too many carries implications. The flood of data will overwhelm resources. Not every object can be studied in detail. Some will be bright enough for chemistry, others too faint. Some will be tracked for weeks, others lost after days. With more arrivals than capacity, choices must be made, and choices create gaps. Those gaps become fertile ground for speculation. If one visitor's spectrum is never fully measured, suspicions will rise that something was hidden. If one trajectory is uncertain, rumours will grow of deliberate motion. Too many arrivals mean too many questions left unanswered, and unanswered questions accumulate into doubt. There is also the practical matter of how humanity prepares for abundance. A few visitors can be followed by dedicated instruments, but dozens will require automated systems, algorithms sifting through torrents of data, selecting which to prioritise. In that automation, nuance may be lost. Anomalies that deserve attention may be flagged as noise, while ordinary cases may consume resources. The threshold of too many risks diluting focus, making it harder to distinguish what truly matters. In the noise of abundance, signals can be missed. The fear is not just that we will have too many to track, but that hidden among them will be one we needed to notice. The cultural dimension of too many cannot be ignored either. Each detection will make headlines at first, but as frequency rises, novelty will fade. News outlets will begin to treat them as routine, reducing coverage to brief notes. The public, once fascinated, may grow numb until one anomaly reignites interest. That anomaly, whatever it is, will be amplified by the backdrop of countless previous arrivals. The narrative will not be that one visitor is strange, but that strangeness emerges out of saturation. Too many becomes the context for paranoia. In that sense, the threshold is not a number, but a shift in attention, when routine turns extraordinary into expectation. The history of astronomical discovery offers parallels. When exoplanets were first found, each was headline news. The first hot Jupiter, the first Earth-like world, the first multi-planet system. Every detection was treated as a milestone. Today, thousands of exoplanets have been catalogued. The flood has turned discovery into routine. Headlines appear only for the rarest cases, yet even in that routine, patterns have reshaped science. The same will happen with interstellar wanderers. Too many will erase novelty but create opportunity. Science will thrive, but public perception will oscillate between boredom and suspicion. Both reactions are dangerous in their own ways. Boredom leads to neglect, suspicion leads to conspiracy. Another threshold lies in risk perception. Interstellar visitors, by definition, move too fast to be bound by the sun's gravity, but some pass within ranges that, if trajectories were slightly different, could bring them close to Earth. The probability of impact is negligible, but not zero. As numbers rise, so do the chances of near misses. A handful of close approaches could transform public perception dramatically. What was once treated as harmless background becomes perceived as threat. Too many near misses, even without actual collisions, would shift the narrative from curiosity to alarm. The threshold is crossed when statistical safety collides with human fear. Speculation thrives in thresholds. Too many arrivals in a short span, too many anomalies in chemistry, too many unexplained deviations in trajectories. Each of these pushes coincidence into doubt. The suspicion that frequency signals intent grows stronger as numbers climb. If 3 in 10 years feel strange, what will 30 in 30 years feel like? The line between random distribution and deliberate sequence will blur, not because the evidence demands it, but because perception insists upon it. At some point, too many will not just mean abundance. It will mean suspicion has become unavoidable. The threshold also matters for how we think about ourselves. Humanity has long imagined itself as central, a focal point in the universe. The Copernican shift displaced us from the centre of the cosmos, but psychologically we still cling to a sense of uniqueness. Interstellar visitors threaten that sense by reminding us that our solar system is porous, that countless fragments from elsewhere drift through constantly, indifferent to our presence. When numbers grow too high, the illusion of isolation collapses entirely. The threshold of too many is not only about objects in the sky, it is about our ability to maintain the story that we are alone. Crossing that threshold will not happen suddenly. It will creep, detection by detection, until the cumulative effect tips the balance. Scientists will announce each new visitor with excitement, but eventually even they will acknowledge the flood. Papers will speak not of singular anomalies, but of statistical distributions. Catalogues will swell with orbits, magnitudes, and compositions. And then, somewhere along that process, the question will shift. No longer will it be, what if another comes? It will be, how do we manage the endless stream? That is the moment when the threshold is passed. Too many no longer means marvel. It means management, suspicion, and the constant awareness that the sky is never empty. Every interstellar visitor we have seen so far has been silent. Oumuamua emitted no signals. Borisov carried no radio patterns. Atlas spoke only through the faint glow of molecules escaping into space. Silence is expected. They are rocks and ice, fragments of planetary systems long forgotten. They do not speak because they cannot. Yet silence is never neutral. When objects pass through our solar system without sound or signal, the absence itself becomes meaningful. We measure their speeds, their chemistries, their trajectories, and in every data set the silence remains, a reminder that the question of intention cannot be answered with confidence. Silence does not prove absence of design. It proves only that nothing has been detected. Astronomers approach this silence pragmatically. Telescopes scan radio bands, searching for coherent transmissions that would distinguish artificial signals from natural noise. None have been found. Observations check for unusual accelerations, maneuvers inconsistent with outgassing or gravity. None have been confirmed. The data support natural explanations, but speculation thrives not in data, but in gaps. When objects move silently through our skies, they create space for questions that science cannot fully close. What if silence is not absence but strategy? What if intention hides not in what is emitted, but in what is withheld? The idea of hidden intention is not new. When Oumuamua's faint non-gravitational acceleration was detected, some suggested it might be a light sail, a probe propelled by starlight. The lack of visible outgassing made the hypothesis tempting, though natural explanations eventually dominated. Still, the debate highlighted a truth. Silence does not erase suspicion. When anomalies appear and silence follows, the gap between evidence and certainty fills with speculation. In that gap, hidden intention becomes plausible enough to linger. The silence of Atlas is similar. Its chemistry surprised astronomers, but no signals, no maneuvers, nothing beyond natural processes were observed. Yet its speed, its composition, its very presence raise questions. If a civilization wished to disguise its probes among natural debris, silence would be essential. An object that emits signals would draw attention. An object that remains quiet, passing as a comet or asteroid, would be invisible within the crowd of natural wanderers. Silence becomes the perfect camouflage. Whether this idea is credible or not, it underscores the unease that accompanies every detection. Intention, if it exists, could be hidden behind silence. Hidden intention need not mean conspiracy. It may be embedded in chemistry rather than in radio waves. A specific ratio of isotopes, a molecule unlikely to form naturally, a pattern in composition that repeats across multiple visitors. Any of these could carry meaning, unnoticed until patterns emerge. Silence at one level could mask subtle signals at another. If intention were ever embedded in the wanderers, it might not announce itself loudly. It would hide in plain sight, relying on us to notice only when our instruments became sophisticated enough. This possibility cannot be dismissed outright because it is consistent with what we already observe. Silence paired with anomalies. But there is a simpler explanation for silence. Survival. Interstellar objects that emit nothing, that make no sound, that drift quietly through the galaxy are more likely to endure. They do not erode energy reserves. They do not expose themselves to predators or collisions. They do not reveal their presence unnecessarily. Silence, in this sense, is a property of endurance. The objects we see are the ones that have lasted, and the ones that have lasted are those that ask nothing of the universe but to drift. Silence is not a strategy, but a consequence of time. The challenge is distinguishing between these frames. To scientists, silence is absence. To imagination, silence is disguise. Both interpretations are reasonable in their own ways, and both will persist as long as the data remain incomplete. The question is whether silence will ever be broken. If one visitor were to emit a coherent signal, or if one were to maneuver in unmistakably artificial ways, then intention would shift from hidden to undeniable. Until then, silence is all we have, and silence is never conclusive. The idea of hidden intentions also shapes how we prepare for the future. If more interstellar visitors are detected, as models predict, then the silence will multiply. Most will pass without incident, their only story written in faint spectral lines. But among the silence, anomalies will emerge, and with them suspicion. If a series of objects arrive with similar chemistries or trajectories, silence will no longer be enough to guarantee dismissal. Patterns will raise questions even when no signals are heard. Silence, repeated too often, may begin to sound like something more. This creates a paradox. The more visitors arrive silently, the stronger both confidence and suspicion become. Confidence, because repeated silence reinforces the natural explanation. Suspicion, because repeated silence in the presence of anomalies begins to feel intentional. The same evidence supports both conclusions depending on how it is framed. Silence is a blank canvas, and onto it we project either randomness or design. The truth is likely simple. These are natural bodies. but simplicity is rarely satisfying when the stakes feel existential. The psychological weight of silence cannot be overstated. Human beings are uneasy in the absence of sound or signal. We look for meaning, and when none is offered, we invent it. In the case of interstellar visitors, the silence of their passage echoes too loudly to ignore. It feels as if the galaxy is withholding something, as if the messengers pass us by without speaking because they are not meant for us, or because we are not ready, or because they are not what we think they are at all. Silence becomes louder than noise, shaping our interpretations more than any signal could. Science will continue to interpret silence as neutrality. Every detection will be catalogued, every spectrum measured, every trajectory calculated. Reports will conclude that no artificial signals were found, no unusual maneuvers detected. Silence will be presented as reassurance. But reassurance has limits. The public will not forget that absence of evidence is not evidence of absence. And with every new silent visitor, the gap between scientific caution and human imagination will widen. Hidden intention will remain possible, even if unlikely, and possibility is enough to sustain speculation. The wanderers remind us that silence itself is a form of presence. They arrive without invitation, move without explanation, and leave without acknowledgement. They do not speak, but their silence shapes us. Whether coincidence or conspiracy, whether natural or intentional, the fact remains that they are here and they are quiet. Quiet enough to make us question what silence really means. Quiet enough to remind us that sometimes what is hidden is not in what is said, but in what is never spoken at all. When Oumuamua first appeared in 2017, one of the earliest questions that circulated outside academic circles was whether it might not be a natural rock at all, but something more deliberate. Its strange shape, its unexplained acceleration, its silence, all combined to create an opening for speculation. What if, some wondered, it was not simply a visitor but a probe, designed to blend in with the countless fragments of rock and ice that populate interstellar space? The idea was dismissed quickly in scientific literature, but it never fully vanished. The reason is simple. If surveillance were ever to come from elsewhere, the most effective disguise would be debris. Debris is everywhere. Asteroids, comets, fragments of collisions, shards ejected from planetary systems. The galaxy is filled with trillions upon trillions of small bodies wandering the void. They are common, expected, and easily overlooked. An artificial probe designed to mimic debris would enjoy near-perfect camouflage. No one would question its presence, because its very existence would align with natural predictions. Its trajectory would be hyperbolic, its chemistry comet-like, its appearance unremarkable. It would drift silently, indistinguishable from the background, and in doing so, it could pass through solar systems unnoticed. Surveillance disguised as debris is not only plausible, it is the logical strategy if stealth is the goal. Astronomers do not operate under this assumption. They study interstellar visitors as natural phenomena, as data points for galactic models. Yet even within that framework, the possibility lingers. The very features that make debris so common also make it the perfect cover. Silence can be explained as natural, but it can also be deliberate. Anomalous chemistry can be explained as exotic origins, but it can also be interpreted as engineering. Unusual speed can be attributed to gravitational scattering, but it can also raise suspicion of propulsion. Every explanation leaves room for alternatives. The disguise works because science cannot conclusively rule out intent without evidence, and evidence is almost impossible to obtain. Consider Atlas, with its surprising carbon dioxide levels. Scientists framed the anomaly in natural terms, but outside those explanations, speculation grew. Could a probe be engineered to carry specific chemistry, either to test our instruments or to conceal machinery beneath layers of ice? The question is not whether this is likely, but whether it is possible. Possibility alone is enough to sustain the suspicion. because if one wanted to observe another civilization, what better method than to send probes designed to look like ordinary debris? Probes that would never trigger alarm until someone noticed a detail that did not quite fit. The challenge is that suspicion cannot be settled by observation alone. Even if a visitor displayed anomalies, those anomalies could always be explained naturally. Oumuamia's acceleration could be due to outgassing too faint to detect. Atlas's chemistry could reflect rare formation conditions. Borisov's similarity to solar comets could reflect universal processes. Nothing requires artificiality, yet nothing fully excludes it either. The disguise works precisely because it aligns with probability. In a galaxy filled with debris, a probe dressed as debris would never stand out, at least not at first glance. Surveillance disguised as debris also offers efficiency. A probe that broadcasts signals risks discovery, interception, or destruction. A probe that drifts silently, blending in with the background, can move freely, gathering data passively. It can rely on civilizations like ours to study it, inadvertently revealing information through the act of observation. Telescopes turned toward Atlas did not simply study it. They broadcasted the presence of an intelligent species curious enough to look closely. If surveillance exists, it may not require active transmission. It may rely entirely on how we react, on what we reveal about ourselves when confronted with anomalies. The debris does not need to speak. We do the speaking ourselves. There is also the question of intent. Surveillance does not necessarily imply hostility. It could mean curiosity, cataloguing, or simple monitoring. A civilization advanced enough to send disguised probes would not need to announce itself. It could observe quietly, gathering knowledge without interference. But the ambiguity is enough to disturb. Surveillance, even if benign, is a violation of comfort. To imagine that every silent wanderer might be more than it appears is to accept that we are not just watched by the galaxy but studied, without consent, without warning. The disguise makes it tolerable for the observer, intolerable for the observed. Skeptics argue that the idea collapses under scale. The galaxy is too large, the number of debris fragments too vast for surveillance to be efficient. Sending probes disguised as debris to every system would be impractical, yet this argument assumes uniformity. Surveillance may not require saturation. A few disguised probes drifting through key regions may be enough. The randomness of arrival may itself be part of the strategy, ensuring that no pattern is obvious, that suspicion remains diffuse. Efficiency is relative, and in a galaxy where lifespans of civilizations could span millennia, patience could replace numbers as the tool of surveillance. The deeper problem lies in trust. Science can offer reassurance that natural explanations are sufficient, but reassurance fades when confronted with uncertainty. People do not ask whether something is probable, they ask whether something is possible, and the answer to possibility is always yes. It is possible that some wanderers are not what they appear. It is possible that surveillance hides among silence. It is possible that intent disguises itself as chance. These possibilities cannot be erased, only managed, and managing them requires acknowledging the discomfort rather than dismissing it. The next decades will test this balance. With more detections on the horizon, anomalies will multiply. Some will be trivial, others significant. Each will raise the same question: coincidence or camouflage? Science will lean toward coincidence, but speculation will lean toward disguise. Public imagination will not be satisfied with natural explanations alone. Every unusual chemistry, every unexpected acceleration, every silent passage will invite whispers of surveillance. Even if none are probes, the suspicion will grow, fed by frequency, sustained by silence, reinforced by our inability to prove otherwise. And if even one visitor were to break the silence, to emit a coherent signal, to maneuver deliberately, to display isotopes unlikely to form naturally, then the disguise would be pierced. One confirmation would retroactively transform all suspicions. Every visitor before, every anomaly noted would be reinterpreted as deliberate. The line between debris and probe would collapse, and trust in natural explanations would erode overnight. The possibility of surveillance disguised as debris is not threatening only because it might be true. It is threatening because if it ever proved true once, it would reshape how we see every object that follows. For now, the safest conclusion is that the wanderers are natural, their silence and anomalies products of chance, not disguise. But safety is not certainty. The galaxy does not offer certainty. It offers probabilities, distributions, and gaps in data. Within those gaps, suspicion thrives. Surveillance disguised as debris remains a possibility because debris itself is the perfect cover. And every time a new visitor is discovered, silent, strange, and fleeting, the thought re-emerges. Maybe this one is natural. Maybe all of them are natural. But maybe hidden among the countless fragments is one that is not. The first confirmed interstellar visitor was celebrated as a 1-in-a-million event, a moment so rare that it seemed unlikely to be repeated in our lifetimes. Yet within a few short years, the count rose from 1 to 2, and then from 2 to 3. Now, with better surveys scanning the skies, astronomers predict a steady stream of detections in the years ahead. Each new discovery chips away at the illusion of rarity, replacing astonishment with expectation. An expectation invites a new kind of speculation, not about the objects themselves, but about what their increasing presence implies. Out of that speculation emerges the idea of accumulation, that the more of these wanderers pass through our solar system, the more likely it becomes that one will linger, one will collide, or one will reveal something we cannot ignore. The accumulation hypothesis is not about inevitability in the strict sense. It does not say that a particular outcome must happen at a particular time. Instead, it reframes the problem in terms of statistics. If trillions of interstellar fragments wander the galaxy, and if even a small fraction of them pass through our system, then every encounter adds to the cumulative odds that one will be unusual. One might carry chemistry never seen before. One might pass close enough to be studied in detail. One might strike a planet or a moon. One might even display behaviour inconsistent with natural origins. Each detection increases the total opportunity for anomalies, and with enough opportunities, anomalies become certainty. For astronomers, this logic is both exciting and daunting. The more objects we find, the more likely we are to discover something that challenges our models of planetary formation. The chemistry of Atlas already did so, forcing scientists to question assumptions about volatile ratios. The elongated shape and acceleration of Oumuamua pushed the boundaries of explanation. Borisov, reassuringly comet-like, reminded us that some wanderers align with expectations. Together, these three already illustrate the principle of accumulation. Each new object multiplies the possibilities, each new data point complicates the picture. With 10 or 20 visitors, the range of outcomes will grow dramatically. Science thrives on such growth, but it also risks being overwhelmed by it. From a broader perspective, accumulation raises practical concerns. The more wanderers that pass through, the greater the chance that one will intersect Earth's orbit in dangerous ways. The odds are still vanishingly small on human timescales, but not zero. Over millions of years, an impact becomes plausible. If interstellar debris is truly as abundant as models suggest, then accumulation guarantees that Earth and other planets will eventually be struck. In fact, some hypothesize that past impacts may already have been caused by interstellar objects, their alien chemistry buried deep in craters we have yet to analyze fully. The idea that accumulation could bring not just knowledge but danger is a reminder that frequency is not neutral. More is not always safer. Accumulation also applies to perception. Each detection adds weight to the cultural narrative of interstellar visitors. 1 detection was exciting, 2 was affirming, 3 already invites speculation about intent. With 10 or more, the story will shift again. People will begin to treat them not as rare visitors, but as a new category of presence. That presence, whether seen as benign or threatening, will reshape how humanity sees the sky. The more silent wanderers pass by, the harder it will be to dismiss the idea that something larger is at play. Accumulation changes meaning, not just in science, but in society. There is a further layer to the hypothesis: accumulation of anomalies. Natural variation explains much of what we see, but anomalies attract disproportionate attention. Each time a visitor displays something unexpected, it is catalogued, debated, sometimes dismissed. But the anomalies do not disappear. They accumulate in memory, building a record of strangeness. Oumuamua's acceleration remains unresolved. Atlas's carbon dioxide levels remain unusual. Future visitors will bring their own puzzles, and together these puzzles will form a list too long to ignore. Individually, each anomaly can be explained. Collectively, they begin to look like a pattern. The accumulation hypothesis suggests that even if every anomaly is natural, their sheer number will force us to reconsider how we interpret them. The most speculative version of the hypothesis imagines that accumulation is not random at all. Instead of countless wanderers passing by without purpose, what if their increasing presence signals surveillance or intention? In this view, the accumulation of visitors in our era is not coincidence but design, a gradual build-up meant to test, monitor, or prepare. The possibility is remote, but it gains traction because of perception. As more objects are discovered, the more the narrative of build-up feels persuasive, even if statistics explain it cleanly. The accumulation of suspicion grows alongside the accumulation of detections. Both are inevitable, even if unrelated. The hypothesis also intersects with survival. If interstellar objects carry organic compounds or even microbial life, then accumulation becomes a mechanism for panspermia, the spread of life across the galaxy. A single visitor may or may not carry viable material, but billions over billions of years make it nearly certain that some do. Each passage is a chance for impact, for transfer, for seeding. Life on Earth may itself be the product of such accumulation, the outcome of countless silent messengers passing through until one delivered the right ingredients at the right time. In this framing, accumulation is not a warning but an origin story, a reminder that our existence may be the result of statistical inevitability. Yet accumulation is also about limits. As detections grow, resources will strain. Astronomers cannot study every visitor in detail. Some will be missed, others observed only briefly. The flood of data will outpace our ability to process it. This too is a kind of accumulation, not of objects, but of gaps in knowledge. Each missed opportunity adds to the pile, each unanswered question compounds. The more we detect, the more incomplete our understanding becomes. Accumulation guarantees both growth and deficit, progress and frustration. Psychologically, the threshold of too many and the accumulation hypothesis overlap. Both ask how abundance changes meaning. Too many speaks to perception, the sense of being overwhelmed. Accumulation speaks to inevitability, the certainty that rare outcomes become probable with enough trials. Together they form attention. More detections mean more knowledge, but they also mean more suspicion, more danger, more unanswered questions. The accumulation hypothesis forces us to accept that the story of interstellar visitors will not remain static. It will intensify with time, and in that intensity, both wonder and paranoia will grow. The wanderers that pass through our skies are not coordinated, at least not in ways we can prove. But their accumulation creates the illusion of coordination, the sense of a pattern building. Each new detection is another layer, another reminder that we are not isolated. Whether natural or not, the cumulative effect is the same. We begin to feel watched, studied, or at least surrounded. Accumulation transforms probability into presence, and presence, when multiplied enough, becomes impossible to ignore. The phrase dark forest comes from a metaphor about the nature of civilizations in the galaxy. It imagines the universe as a vast forest filled with hunters, each one armed, each one silent, each one unsure of the intentions of others. In such a forest, the safest strategy is to remain hidden. To announce oneself is to risk being noticed by an unknown presence that may not be friendly. Silence is survival, and suspicion is the rule. This metaphor, while speculative, has found a foothold in discussions about interstellar visitors, because their arrival forces us to confront the uncomfortable possibility that we may not be as alone as we imagine. And if we are not alone, then every fragment drifting into our solar system may be something more than debris. They may be echoes of civilizations following the same logic, hiding in plain sight, watching without being seen, camouflaged against the noise of natural wanderers. Oumuamua sharpened this tension. Its unexplained acceleration, its unusual shape, and its silence fit into a pattern that could be interpreted either as coincidence or as caution. If it were artificial, then its disguise as debris would have been perfect, exactly the sort of camouflage one would expect in a galaxy where exposure is dangerous. Borisov, by contrast, reassured observers with its comet-like features. It looked like natural debris, and its chemistry fit neatly into astrophysical models. Atlas unsettled the balance again, reminding us that not all chemistry aligns with expectations. This sequence mirrors the dark forest metaphor itself. Moments of reassurance broken by moments of suspicion, silence layered with anomalies, uncertainty that never resolves completely. When interstellar visitors become frequent, the metaphor grows heavier. In a galaxy filled with wanderers, the dark forest is not empty. It is crowded. Every detection adds to the sense that we are surrounded by movements we cannot control, by presences we cannot interrogate, by fragments we cannot fully explain. The forest is not dark because it is silent. It is dark because we cannot tell which silences are natural and which are deliberate. We cannot tell which shadows are trees and which might be hunters. The more visitors pass through, the wider the forest seems to stretch, and the less certain we become about what moves within it. This is where the danger of interpretation lies. If every visitor is assumed natural, we risk overlooking signals of something more. If every visitor is assumed deliberate, we risk drowning in paranoia. The truth may lie somewhere in between, but the dark forest metaphor insists that we may never know. Ambiguity is part of the environment. In a setting where silence is survival, every fragment could be both natural and not, both innocent and dangerous. Certainty is impossible, suspicion is unavoidable. The forest opens wider not because the visitors are coordinated, but because their presence magnifies our awareness of how little we understand. The dark forest metaphor also reframes silence itself. To us, the absence of signals feels empty, but in the metaphor, silence is a strategy. If civilizations exist, they remain quiet to avoid attention. If probes exist, they disguise themselves as debris. If signals are sent, they may be hidden in chemistry, in isotopic ratios, in patterns we do not yet know how to read. Silence, in this view, is not absence but camouflage. The more silent wanderers we detect, the more the forest feels populated, not by voices shouting across the void, but by presences crouched in shadows, observing without revealing themselves. This does not mean that every interstellar object is a probe. The overwhelming majority are almost certainly natural. But the metaphor changes how we experience them. In a galaxy imagined as a dark forest, even natural debris becomes part of the atmosphere of suspicion. Every fragment drifting into our solar system reminds us that the forest is active, that silence is not emptiness, that presence does not require introduction. The dark forest opens wider with each detection, because each detection expands the range of possibilities we must consider. From a scientific perspective, the metaphor complicates interpretation. Astronomers must remain grounded in data, cautious in speculation, but the dark forest idea presses against that caution, forcing them to acknowledge that some questions cannot be settled with evidence alone. Silence cannot prove absence, anomalies cannot prove intent. The line between coincidence and conspiracy is blurred by the metaphor, which insists that uncertainty is not a temporary problem, but a permanent condition. The forest is not meant to be mapped. It is meant to remain dangerous, filled with unseen presences that never reveal themselves. For humanity, this framing is unsettling because it challenges the optimism that often surrounds the search for extraterrestrial intelligence. Optimism imagines communication, cooperation, shared knowledge. The dark forest imagines survival, suspicion, and silence. Interstellar visitors, silent and ambiguous, seem to embody the latter more than the former. They do not call out to us, they do not linger to be studied, they arrive unannounced and leave without explanation. If they are natural, they fit the metaphor by accident. If they are artificial, they fit it by design. Either way, the forest feels darker with every passing object. The metaphor also shapes how we think about preparation. If the galaxy is a dark forest, then how should we behave? Should we remain silent, avoiding transmissions that might reveal our presence? Or should we embrace transparency, trusting that others may be more curious than hostile? Interstellar visitors amplify this debate. If even debris might be disguised, then caution feels justified. But if all silence is camouflage, then openness might be the only way to break the cycle. The Wanderers force us to confront this dilemma not in abstract terms, but in practical ones, because their presence is not hypothetical. They are here, and their silence forces us to choose how we interpret it. What makes the dark forest metaphor powerful is that it does not require confirmation of other civilizations to feel relevant. It functions even in the absence of evidence, because it describes how we experience uncertainty. The forest is dark because our instruments are limited, because our perspective is narrow, because our ability to distinguish natural from artificial is fragile. The Wanderers exemplify this fragility. We see them briefly, gather limited data, and then lose them to distance. Each one could carry the memory of another system or the intention of another civilization, and we would never know. The darkness is not in the galaxy itself, but in our inability to see clearly. As detections increase, the forest will seem to grow more crowded. Each new visitor adds another shadow, another presence we cannot fully explain. The cumulative effect is not simply knowledge but atmosphere. The sense that the galaxy is alive with motion, silent and ambiguous, never offering clarity. The dark forest opens wider, not because the visitors multiply, but because our awareness of them does. The forest has always been there. What changes is that we now see the edges of it, and in seeing, we imagine what lies beyond. The unsettling truth is that the metaphor may always remain metaphor. We may never know if civilizations exist, if probes are hidden, if silence is camouflage. But the Wanderers ensure that we will never escape the feeling of the forest. Their presence is enough to remind us that the galaxy is not empty. Whether filled with debris or with watchers, the effect is the same. The forest is wide, the forest is dark, and we are inside it, unable to tell who else may be moving in the shadows. When astronomers point their instruments toward an interstellar object, the first thing they look for is movement. Trajectory confirms origin. Speed confirms that it cannot be bound to the sun. The next thing they look for is light, broken apart by spectrographs into lines that reveal composition. But what they are really searching for, often without saying it aloud, is meaning. Every line of chemistry, every mineral signature, every volatile escaping into a faint tail is treated not just as data, but as potential message. Because the possibility lingers that the materials themselves could carry signals, not signals in the form of radio waves or flashing lights, but signals embedded in the stone, encoded in the ice, hidden in ways only science can reveal. the idea is not purely speculative. Nature already carries messages in matter. Isotopic ratios tell us about the age of stars. Mineral compositions reveal the environments of formation. Even the simple presence of water ice is a statement about temperature and distance from a star. Every piece of debris is, in this sense, a letter from its birthplace, carrying within it the conditions of a system we may never visit. When Borisov showed familiar cometary chemistry, it was a message of reassurance, a reminder that processes in our solar system are not unique. When Atlas displayed unexpected levels of carbon dioxide, it was a message of surprise, a reminder that other systems may follow paths we do not anticipate. In stone and ice, there is already language, one we are only beginning to learn how to read. But language in this sense is ambiguous. A high concentration of carbon dioxide could be a natural product of formation, or it could be a deliberate marker placed to test our recognition. An unusual ratio of isotopes could be coincidence, or it could be a code designed to stand out against background distributions. The ambiguity is inescapable because matter is both natural and malleable. To read signals in stone is to walk the line between geology and intention, chemistry and communication. The very features that make natural explanation strong also make deliberate encoding plausible, at least in theory. The thought of language in ice raises questions about what form such communication would take. If a civilization wanted to leave enduring messages, what medium would they choose? Electromagnetic signals degrade over time, structures decay. But ice and rock endure, drifting for billions of years through interstellar space. A probe disguised as a comet could last long enough to cross the galaxy. Its chemistry could be engineered to carry patterns unlikely to occur by chance, patterns that could only be recognized by a species with advanced instruments. In this way, the Wanderers could be libraries, their molecules arranged as words, their isotopes arranged as syntax, their presence a form of cosmic writing. Skeptics argue that this is anthropocentric, projecting our own methods of communication onto hypothetical others. But the principle is sound. Matter carries information, and information can be arranged. Whether intentionally or not, interstellar debris already transmits signals through its structure. A shard of metal forged in a star carries a signature that reveals the star's processes. A grain of dust frozen in a comet's heart carries the memory of temperature and pressure at its formation. These are natural signals, unintentional but real. The question is whether intention might one day be found layered atop them, hidden in the stone and ice of a visitor that refuses to match our models. The danger of this line of thought is overinterpretation. Human beings are pattern seekers. We find meaning in randomness, signals in noise, design in accident. A faint deviation in a spectral line could be chemistry, or it could be calibration error. A strange mineral could be an ordinary product of physics, or it could be misidentified in the rush of observation. The possibility of language in ice tempts us to treat every anomaly as code. Without discipline, science can slip into speculation, and speculation can slip into paranoia. The line between discovery and projection is thin, yet to dismiss the possibility outright would be equally dangerous. If signals could exist in stone and ice, then ignoring anomalies risks overlooking genuine messages. This is the paradox. We must search without assuming, interpret without projecting, remain cautious without closing the door. The Wanderers demand this balance because they bring with them both data and mystery. Every detection is both ordinary and extraordinary, both natural and potentially more. Signals in stone may be nothing, or they may be everything, and the only way to know is to keep reading. Consider the history of meteorites on Earth. Some contain amino acids, simple organic molecules that are precursors to life. These are natural products of chemistry, but when first discovered, they sparked debates about panspermia and the possibility that life itself could have been seeded by such fragments. Even now, the line between natural and intentional remains blurred. If interstellar visitors carry organics, as Borisov likely did, then they too carry signals, signals not in words, but in the building blocks of biology. If such molecules arrive frequently enough, then life could spread across the galaxy through stone and ice. In that sense, the Wanderers are already messengers, whether or not anyone designed them to be. Atlas sharpened this question further. Its unusual chemistry suggested conditions different from any we had expected. Some scientists saw this as confirmation of diversity in planetary systems. Others noted that its ratios were so unusual that they might serve as markers. The line between natural anomaly and deliberate signal blurred once again. If a civilization wished to test whether others were watching, what better method than to send fragments with chemistries just strange enough to raise questions? They would pass unnoticed by most, but for those with instruments, the anomaly would stand out. The stone and ice would carry language, not by spelling out messages, but by deviating just enough from expectation to demand attention. This is why every new detection matters. Each visitor expands the library of signals, whether natural or not. By comparing them, we begin to see distributions. Most will cluster around natural expectations. A few will stand apart. Those outliers may be rare, but are also the most important. They are the ones that challenge our assumptions, the ones that force us to decide whether we are seeing coincidence or communication. The accumulation of anomalies, as discussed before, becomes the test. If enough visitors deviate in ways that cannot be dismissed, then the possibility of language in ice will grow harder to ignore. In the meantime, the signals remain ambiguous. A comet flares with carbon dioxide. A fragment accelerates faintly without explanation. A shard of stone reveals isotopes that do not match expectations. Each one is both message and noise, both data and doubt. The Wanderers keep their language hidden, or perhaps they have no language at all, and we are the ones inventing it. The truth is unknowable for now, but the act of looking, of reading spectra and cataloguing anomalies is itself a kind of dialogue. We ask questions, the sky responds with silence, and in that silence we find signals anyway. What matters is that the search continues. Whether signals in stone are natural or deliberate, they expand our understanding of the galaxy. They teach us about diversity, about chemistry, about the possibilities of life. They remind us that information is carried not only in light and sound, but in the very fabric of matter itself. A fragment drifting across the void is not empty. It is filled with history, with memory, with the potential for meaning. To see it as debris is to see only half the story. To see it as language is to admit that the universe may be speaking in ways we do not yet understand. When we look at interstellar visitors, it is tempting to believe that we are studying them. We measure their speed, we track their paths, we break down their light into spectral lines to see which molecules they carry. But in reality, the story they tell is as much about us as it is about them. The way we interpret Oumuamua, Borisov, Atlas, and the others yet to come is shaped not only by data but by our own expectations, fears and desires. The sky, filled with these fleeting wanderers, becomes a mirror in which we see reflected the contours of our own uncertainty. Take the first detection. Oumuamua entered the solar system in 2017 and was gone before we could study it in depth. It left behind more questions than answers, an unusual shape, a strange acceleration, a silence that fueled speculation. Some saw in it the possibility of alien technology, a probe passing by unnoticed until our telescopes caught it too late. Others insisted on natural explanations, pointing to outgassing too faint to detect, or to fragmentation that might account for its acceleration. The object itself offered only silence, yet the reaction revealed something about us. We're quick to wonder if we're being watched, quick to suspect intention when faced with anomaly, quick to project meaning onto silence. The mirror showed us our readiness to see ourselves in what we do not understand. Then came Borisov in 2019. Unlike Oumuamua, it looked familiar. A comet with a tail, shedding dust and gas in ways that aligned with models. Its chemistry was different in detail, but recognizable in kind. For scientists, it was reassuring. For the public, it was a relief. The mirror reflected a different part of us this time. Our desire for normalcy, for the comfort of continuity. The narrative shifted from suspicion back to familiarity. We wanted the cosmos to surprise us, but not too much. We wanted to see the exotic, but only within the bounds of what we already knew. Borisov allowed us to look into the sky and see stability reflected back. Atlas unsettled the balance again. Its carbon dioxide levels, far higher than expected, stood out as anomalous. Its faintness and speed made it difficult to study in detail, but what little was captured pointed to something unusual. For scientists, this was exciting, a chance to expand understanding of how planetary systems form. For others, it was disquieting. The mirror reflected our unease with patterns that break too sharply from expectation. Just as Borisov had reassured us, Atlas reminded us that strangeness remains. We want discovery, but we do not want too much strangeness at once. Each detection forces us to confront the limits of how much deviation we are willing to accept before suspicion returns. The sequence shows how the visitors themselves are less important than the way we respond to them. Oumuamua was ambiguous, and so we projected both awe and paranoia. Borisov was ordinary, and so we projected relief. Atlas was anomalous, and so we projected caution. In each case, the mirror revealed us. It showed our hunger for contact, our craving for reassurance, our fear of the unknown, our tendency to drift between science and speculation, depending on how much data we had and how well it fit our models. The sky does not tell us who we are directly, but in the way we interpret its messengers, we see ourselves clearly. This mirroring effect becomes more pronounced as detections increase. With each new visitor, society will divide along predictable lines. Some will lean towards scientific caution, emphasizing natural explanations. Others will lean toward imaginative speculation, seeing hidden intent behind every anomaly. Still, others will drift between the two, depending on the balance of evidence. The wanderers themselves remain silent, but the debates they spark expose our divisions, our hopes, and our fears. They become canvases onto which we paint our own narratives. In that sense, they are less like intruders from the galaxy, and more like reflections of our internal conflicts. The sky has always served as a mirror. Ancient cultures saw in the constellations the stories they needed to tell. Hunters, animals, gods, myths that reflected their values and fears. Comets were omens, meteors were messages, eclipses were warnings. Today, with interstellar visitors, the pattern repeats, only with scientific data in place of myth. We look at spectra and trajectories instead of star patterns, but the impulse is the same. We search the sky not only for answers about the universe, but for answers about ourselves. The mirror changes shape, but it remains a mirror. This is why anomalies matter so much. A perfectly ordinary comet like Borisov reassures us, but does not force reflection. An anomalous visitor like Atlas compels us to confront our discomfort with uncertainty. Oumuamua, in its silence, forced us to face our paranoia. Anomalies are not just puzzles for scientists to solve. They are provocations that reveal the boundaries of our tolerance for ambiguity. Each one shows us how much strangeness we are willing to accept before we start imagining intention. The mirror reveals the tipping point between curiosity and fear. The same is true at the cultural level. Media coverage of interstellar visitors reflects public appetite for mystery. Oumuamua was framed as a possible alien probe because that story resonated with our need for drama. Borisov received less attention because its story was familiar, and familiarity does not sell. Atlas, with its chemical oddities, reignited headlines precisely because it unsettled. The mirror showed us our hunger for narrative, our bias towards stories that emphasize the extraordinary over the ordinary. The visitors are real, but the stories we tell about them are our own, reflected back through the lens of the sky. Even the scientific community is not immune. Theories proliferate not only because of data, but because of intellectual culture. Some push for conservative explanations, others for bold ones, each reflecting broader attitudes about risk, evidence, and imagination. Oumuamua's debates about natural versus artificial origins expose not only the limits of data but the differences in how scientists see their role. Should they push boundaries, or should they restrain speculation? The mirror reflected not just humanity in general, but the character of science itself, torn between caution and curiosity. The mirror effect will only intensify as detections increase. When dozens of wanderers are catalogued, the distribution of responses will grow richer. Some will be ignored as routine, others will be celebrated as breakthroughs. A few will become lightning rods for speculation. In every case, the mirror will show us more: how quickly we grow bored with routine, how excited we become by anomaly, how suspicion grows in the absence of certainty. The objects themselves will remain silent, but the stories we project will grow louder. Ultimately, the wanderers teach us that the universe is not only out there, it is also inside us, in the ways we interpret what we see. The sky becomes a stage, and we project onto it our own fears of being watched, our hopes of contact, our discomfort with uncertainty, our craving for reassurance. The visitors themselves are indifferent. They drift through, shaped by forces billions of years old, carrying no intention, no message. But in their silence, they reflect us back to ourselves. The sky's a mirror, and we are what it shows. The story of interstellar visitors has, from the beginning, been a story caught between two ways of thinking. On one side lies science, careful and methodical, demanding evidence before drawing conclusions. On the other lies paranoia, quick to fill gaps in knowledge with suspicion, imagination, and fear. The meeting point of these two modes of thought is not a comfortable one. It is a space where data and speculation collide, where silence becomes louder than signal, where anomalies refuse to settle into safe categories. Every time a wanderer enters our solar system, this collision repeats. Science measures, paranoia interprets. The two do not cancel each other. They coexist, each shaping how the other is understood. When Oumuamua was first detected, scientists rushed to calculate its orbit, measure its brightness, estimate its size. The data pointed clearly to an interstellar origin, the first of its kind confirmed. But then came the details that science struggled to explain: the elongated shape, the lack of a visible coma, the faint acceleration that could not be accounted for easily by gravity alone. Science proposed natural explanations, but the data were too limited to confirm them. Into that gap stepped paranoia, asking whether the object was artificial. The suggestion that it could be a probe was speculative, but it resonated. It gained traction not because evidence supported it, but because science could not close the case. The absence of certainty became fertile ground for suspicion. Borisov shifted the balance back towards science. Its cometary tale, its dust and gas, its chemistry, all were consistent with natural expectations. Here was an interstellar object that looked like what models predicted. Science took confidence from it. But even then, paranoia was not absent. The fact that it appeared so soon after Oumuamua led some to question whether the timing itself was suspicious. Why did two arrive in such quick succession, after centuries of none being seen? Science pointed to improved surveys, but paranoia pointed to coincidence. The data reassured, but not enough to silence all doubt. The mirror of the sky reflected both relief and suspicion, each strengthened by the presence of the other. Atlas reignited the tension. Its carbon dioxide levels did not match models. Its chemistry stood apart, demanding new explanations. Science framed this as diversity, as a sign that planetary systems can form under conditions unlike those in our own. Paranoia framed it differently, as a deliberate anomaly, a marker, a test. Once again, the data did not fully settle the debate. Once again, the absence of certainty became a stage where science and paranoia confronted one another, and once again, neither side could erase the other. This pattern reveals a deeper truth. Science and paranoia are not separate conversations. They are linked, each responding to the gaps left by the other. Science insists on caution, on probabilities, on waiting for more data. Paranoia thrives precisely because data are limited, because gaps exist, because certainty is slow. The two are not equal in credibility, but they are equal in persistence. As long as the wanderers arrive silently, as long as anomalies remain unexplained, science will never fully quiet paranoia, and paranoia will never fully displace science. The two meet in every detection, locked in an uneasy dialogue. The challenge is that the public does not distinguish between them easily. When scientists speculate cautiously about natural explanations, their caution can sound like uncertainty. That uncertainty feeds paranoia, which thrives on the perception that experts are hiding something or refusing to say what they really think. Conversely, when scientists speak confidently, their confidence can sound like dismissal, which feeds suspicion that anomalies are being ignored. In both cases, the space between science and paranoia widens, even as the two remain entangled. The more wanderers arrive, the more this dynamic will play out in public view. History offers parallels. The discovery of pulsars in the 1960s was a moment when science and paranoia collided in similar ways. The signals were regular, precise, unlike anything seen before. For a brief moment, some astronomers consider the possibility of artificial origin. They jokingly label the first source LGM-1 for little green men. When more pulsars were discovered, the natural explanation became clear: rotating neutron stars. But in that brief window before certainty, paranoia had a foothold. The same dynamic repeats with interstellar visitors. Each new anomaly creates a window where natural explanations are possible but not proven, and in that window, paranoia grows. The danger is not only that paranoia thrives in the absence of certainty, it is also that paranoia feeds on abundance. The more anomalies accumulate, the easier it becomes to weave them into a narrative of intent. One unexplained acceleration is puzzling. Two unusual chemistries are intriguing. Three in a row begins to feel like pattern. Science sees each anomaly as a separate case, each requiring its own explanation. Paranoia sees them as connected, as evidence of conspiracy or surveillance. The difference is one of framing, and framing often matters more than facts in shaping perception. Science has its own limitations in this dynamic. Astronomers cannot collect perfect data. Telescopes miss opportunities. Observations are brief. Instruments have limits. Reports take months or years to publish, leaving long gaps during which speculation fills the silence. By the time natural explanations are carefully laid out, paranoia has already built its narrative. The two do not operate on the same timescale. Science is slow, paranoia is immediate, and in a world where immediacy dominates, the slow voice of science is often drowned out, even if it is more accurate. The collision of science and paranoia will intensify as detections increase. With each new interstellar visitor, new anomalies will emerge. Most will be explainable within natural frameworks, but some will resist. Each resistance will open the same window, the same gap where suspicion thrives. Over time, the weight of accumulated anomalies may become too heavy for public perception to dismiss. Even if science continues to explain each case, paranoia will interpret the accumulation as proof. The two will meet again and again, and each meeting will reinforce the sense that science alone cannot settle the matter. The consequences of this meeting are significant. Public trust in science is shaped not only by data but by perception. If paranoia grows unchecked, it can erode confidence, leading people to believe that anomalies are being hidden or explanations manipulated. If science dismisses paranoia too harshly, it risks alienating those who find speculation compelling. The challenge is to maintain balance, to acknowledge uncertainty without surrendering to fear, to emphasize evidence without denying the possibility of unknowns. The Wanderers force this balance upon us. They are silent enough to invite paranoia, real enough to demand science, and ambiguous enough to ensure that neither can fully dominate. In a way, the meeting of science and paranoia is itself a reflection of the universe we inhabit. The galaxy is vast, filled with possibilities. Some are natural, others remain speculative. The Wanderers remind us that certainty is rare, that knowledge is incomplete, that we are always interpreting fragments. Science gives us tools to measure. Paranoia fills the silence with story. Together they shape how we see ourselves in the cosmos. Neither alone is enough. Together they form the uneasy dialogue that defines our relationship with the unknown. From the moment the first interstellar object was confirmed, humanity was pulled in two directions at once. On one side, curiosity demanded more observations, more data, more chances to learn about the galaxy beyond the reach of our spacecraft. On the other side, fear whispered reminders that these objects are strangers, intruders from the unknown, moving silently through our solar system without explanation. Curiosity and fear are not opposites in this context. They are parallel reactions, each growing stronger as more wanderers are detected. To understand how we respond to these visitors is to recognize that we live constantly at the intersection of those two forces. Curiosity was immediate with Oumuamua. The speed alone was enough to excite astronomers. It could not be bound to the sun. It had come from elsewhere, and it was leaving just as quickly. Never before had we seen such a thing, though models had predicted they must exist. Telescopes across the world turned toward it, racing against time as it faded. But curiosity was frustrated by the brevity of the encounter. By the time the scientific community grasped what it was, Oumuamua was already too faint for detailed study. The frustration only deepened curiosity. We had seen a glimpse of something extraordinary, and then it was gone, leaving behind more questions than answers. But fear was present as well, though more subtle at first. Its strange acceleration unsettled astronomers. Its elongated shape made it difficult to categorize. Its silence left open the question of intention. For some, these details raised the possibility of artificial origin. Even those who dismissed that idea admitted that the object was unlike anything seen before. Curiosity wanted more data. Fear reminded us of how little we understood. The balance between the two shaped the narrative. Awe at the discovery, unease at the mystery. Borisov tilted the balance back toward curiosity. Here was an interstellar object that looked familiar. Its coma, its tail, its chemistry, all consistent with comets in our own solar system. Scientists were able to observe it in more detail than Oumuamua, and the data reinforced models rather than challenging them. Curiosity thrived on the chance to compare, to learn, to confirm predictions. Fear receded, though not entirely. The timing of two detections so close together kept suspicion alive, but Borisov was, in many ways, a reassurance. It showed that not every visitor was anomalous. Some were exactly what science expected. Atlas shifted the balance again. Its high levels of carbon dioxide stood out as unusual, a puzzle not easily explained. For astronomers, this was another reason to be curious. For the public, it stirred unease. Anomalies always do. Each deviation from expectation becomes a seed of fear, because it reminds us that not everything is understood. The more anomalies accumulate, the harder it is to maintain reassurance. Curiosity thrives on puzzles, but fear thrives on patterns, and both were present in the reaction to Atlas. The tension between curiosity and fear is not unique to astronomy. It is part of how humans respond to the unknown in every context. Exploration is always double-edged. We want to know more, but we worry about what we might find. The sea was once filled with monsters in the imagination of sailors. The wilderness was once seen as both opportunity and threat. The sky is no different. Interstellar visitors embody that duality perfectly. They are opportunities to expand knowledge, but also reminders that the universe is filled with forces and objects beyond our control. Science itself reflects this balance. Astronomers push for more surveys, more sensitive instruments, more chances to detect and study wanderers. The Vera Rubin Observatory, expected to discover many such objects in the coming years, is a monument to curiosity. But behind the optimism lies an awareness that detection also brings risk. If even one interstellar object were on a collision course with Earth, the consequences could be catastrophic. The odds are low, but not zero. Each new detection is both a triumph of curiosity and a reminder of vulnerability. The balance is woven into the very act of looking. Public reaction amplifies the tension. Media coverage often leans toward the extraordinary, emphasizing mystery, anomaly, or danger. Stories about alien probes attract more attention than stories about routine cometary behavior. This skews the balance toward fear in public perception, even when science leans toward curiosity. At the same time, the very fact that the public pays attention reflects deep curiosity. People want to know about these visitors, even if what they learn unsettles them. The balance is dynamic, shifting from awe to fear and back again, depending on how the story is told. As detections increase, the balance will be tested further. Routine visitors will normalize curiosity, turning interstellar objects into standard entries in catalogues. But anomalies will stand out more sharply against that backdrop, and each will carry disproportionate weight. Fear does not require frequency. It requires focus. A single anomaly, amplified by media, can shift perception dramatically. Curiosity may thrive on the accumulation of data, but fear thrives on exceptions. The balance will be defined not by the majority of detections, but by the few that resist easy explanation. The cultural consequences are significant. If curiosity dominates, interstellar visitors will be seen as milestones in exploration, opportunities to expand human knowledge, and steps toward understanding our place in the galaxy. If fear dominates, they will be seen as threats, intrusions, or signs of hidden surveillance. Both interpretations are possible, and both will coexist. The balance will shift depending on the context, the anomalies, the stories told. The visitors themselves will not change. What will change is how we see them, and how we see ourselves in relation to them. The balance is fragile because it rests on incomplete knowledge. Science is cautious, always leaving room for uncertainty. Fear exploits that uncertainty. Curiosity seeks to fill it. Neither can eliminate the other. The wanderers guarantee that both will remain present, because they arrive silently, stay briefly, and leave without answering the questions they raise. We are left with fragments, and fragments are enough to sustain both curiosity and fear indefinitely. In the end, the balance between curiosity and fear is not something to be resolved. It is something to be managed. Both are necessary. Curiosity drives discovery. Fear enforces caution. Together, they ensure that we pursue knowledge without recklessness, and that we approach mystery without paralysis. Interstellar visitors remind us of this balance because they embody it so perfectly. They are silent messengers from beyond, both invitations to explore and reminders to beware. The balance is not a flaw in how we respond. It is the condition of being human in a universe that is larger, stranger, and more silent than we can fully understand. The first detection was a surprise. The second was validation. The third was the beginning of a pattern. But as the years pass and surveys improve, interstellar visitors will no longer be rare headlines. They will become a constant background in astronomy, a stream of object entering, passing through, and leaving our solar system in numbers too large to treat as anomalies. What was once extraordinary will become routine. The question is no longer whether more will come, It is how we prepare for the reality of endless arrivals. Preparation begins with infrastructure. The instruments we have today were designed to survey asteroids and comets bound to the sun, not fragments crossing from other stars. Oumuamua was already leaving by the time it was recognized for what it was. Borisov was caught early enough for observation, but only because its coma made it obvious. Atlas was faint and fast, a challenge even with advanced telescopes. If we're to handle endless visitors, we will need dedicated systems to detect them early, track them consistently, and gather data before they vanish into the darkness again. The Vera Rubin Observatory is one step, with its wide field and rapid coverage, but it will not be the last. Networks of telescopes, automated systems, and perhaps even space-based observatories will be required to keep pace with the flow. But infrastructure is only part of preparation. The next challenge is prioritization. Not every visitor can be studied in equal detail. Some will be too faint, others too fast, and resources will always be limited. Decisions will have to be made about which to follow most closely. Do we focus on the brightest, the strangest, the closest? Each choice carries consequences. Focus too narrowly, and we risk missing anomalies. Spread resources too thin, and we risk collecting too little on any single object. Preparing for endless visitors means developing strategies to manage abundance, not scarcity. The difficulty lies in the fact that abundance can be as overwhelming as rarity. Preparation also requires new models of collaboration. Individual observatories cannot handle the flow alone. The global astronomical community will need to share data more efficiently, coordinate observations more tightly, and integrate findings more quickly. What was once the work of scattered teams will become the work of a global network. This collaboration will not be purely scientific. Public communication will be part of it, because as visitors become more frequent, public interest and suspicion will grow. Scientists will need to balance transparency with caution, clarity with complexity. Endless visitors mean endless opportunities for misunderstanding, unless preparation includes strategies for communication as well as observation. Beyond science, preparation has psychological and cultural dimensions. Humanity has always been shaped by how it interprets the sky. The sudden appearance of a comet once sparked fear and prophecy. Today, interstellar objects risk becoming the new symbols around which culture projects meaning. Some will see them as benign, others as threatening, still others as indifferent. Preparing for endless visitors means preparing for the narratives that will emerge, the stories people will tell, the fears they will nurture. Without preparation, the flood of arrivals could deepen paranoia, amplify conspiracy theories, and strain public trust in institutions tasked with explaining the unknown. Then there is the question of risk. Most interstellar visitors will pass safely through the solar system, unnoticed by anyone outside the astronomical community. But with enough arrivals, the odds of close approaches rise. Even if the probability of impact remains low, the sheer number of opportunities guarantees that one day, one object will pass uncomfortably close to Earth. Preparing for endless visitors means preparing for that inevitability. Impact monitoring systems will need to account not just for asteroids bound to the Sun, but for hyperbolic trajectories that sweep in from the stars. Deflection strategies, if ever developed, will have to consider the unique challenges of objects moving far faster than anything native to our system. Endless visitors carry endless potential, and some of that potential is danger. Preparation also involves rethinking what we want from these encounters. Do we merely catalogue them, or do we attempt to intercept them? A spacecraft mission to an interstellar visitor would be extraordinarily difficult, requiring high speeds and precise timing, but not impossible. Proposals already exist for rapid response missions, small spacecraft designed to launch within years of detection and intercept objects before they leave. Preparing for endless visitors means deciding whether we are content to watch them pass or whether we are ready to chase them down. The The choice will define whether the coming era of abundance is one of passive observation or active engagement. Speculation must also be part of preparation. The possibility, however remote, that some visitors are more than natural debris cannot be ignored. Endless arrivals mean endless chances for anomalies. If even one object were ever found to be artificial, the consequences would be transformative. Preparing for endless visitors means preparing not only for scientific puzzles, but for the possibility that one day the puzzles may cross into territory we are not ready to confront. To dismiss that possibility entirely would be reckless. To obsess over it would be paralyzing. The preparation lies in holding both possibilities at once, natural abundance and potential exception, and being ready for either. As the numbers grow, the line between science and culture will blur further. Endless visitors will not remain the exclusive domain of astronomers. They will enter art, literature, media, and politics. They will become symbols of connection or intrusion, opportunity or threat. Preparing for them means more than building telescopes. It means cultivating resilience in how we interpret the unknown, recognizing that curiosity and fear will always coexist, and ensuring that neither overwhelms the other. The flood of arrivals will not only test our instruments, it will test our imagination, our trust, and our ability to remain grounded in a universe that is bigger and stranger than we once believed. Ultimately, preparing for endless visitors is not about reaching a final solution. It is about adapting to a new reality. The solar system is not isolated. It never was. Debris from the galaxy has always passed through. We simply did not see it until now. The change is not in the sky but in us. We are becoming aware of what has always been true. Endless visitors are not a new phenomenon. They are a new perception. Preparing for them means preparing ourselves to live with that perception, with the knowledge that we are surrounded by motion, that the sky is never empty, that the universe does not pass us by but moves through us constantly. The galaxy does not announce itself all at once. It does not open in a single revelation, laying bare its secrets in a way that is immediate and complete. Instead, it reveals itself slowly, indirectly, through fragments that drift across the void and into our awareness. Each interstellar visitor is one of those fragments. They are not emissaries in the deliberate sense, but they are messengers all the same, carrying within them the memory of distant systems, the chemistry of alien skies, the traces of conditions that no telescope on Earth can yet resolve. The universe speaks not in grand declarations, but in small arrivals, one wanderer at a time. Oumuamua was the first to break through the silence of perception. For centuries, astronomers had speculated that interstellar debris must exist, but until it was detected, the idea lived only in theory. Its sudden appearance transformed speculation into evidence. It was a revelation not because it explained the galaxy, but because it proved that the galaxy could reach us in ways we had not seen before. Borisov followed, confirming that such visitors were not a fluke. It showed that what we thought extraordinary was in fact ordinary on the scale of the galaxy. Atlas arrived to complicate the picture, reminding us that variety is the rule, not the exception. Each visitor reshaped our understanding, not through complete answers, but through glimpses. The universe widened incrementally, piece by piece. This incremental revelation is the true significance of the Wanderers. We may never catch one in enough detail to answer every question. We may never find conclusive evidence of life or technology hidden within them, but their accumulation forces us to adjust our perspective. Where once we saw the solar system as self-contained, we now see it as porous. Where once we thought of the stars as distant and unreachable, we now recognize that pieces of them pass through our skies. The Wanderers reveal the galaxy not as something separate from us, but as something that flows through us constantly. The universe is revealed not in an instant, but in a long sequence of arrivals. The process mirrors how science itself works. Knowledge is rarely gained through singular breakthroughs. It is built step by step, observation by observation, anomaly by anomaly. A single detection raises questions, a second provides comparison, a third begins to form a pattern. Over time, the accumulation of fragments becomes a framework. Interstellar visitors follow this pattern. Each one alone is incomplete. Together, they begin to sketch the outline of a larger truth. The universe is too vast to be revealed all at once, but through the steady trickle of wanderers, it reveals itself in ways we can measure, interpret, and slowly begin to understand. The significance of this revelation goes beyond astronomy. It reshapes our place in the cosmos. For centuries, humanity lived with the illusion of isolation. The stars were distant lights, unreachable, untouchable, existing beyond the limits of our world. Even as telescopes improved, the distance remained overwhelming. Interstellar visitors collapse that distance. They are tangible pieces of other systems, crossing the boundary between there and here. Holding data from Oumuamua, Borisov, or Atlas is not abstract. It is direct contact with the galaxy, proof that we are not separate from it but embedded within it. The universe reveals itself not in theory, but in stone and ice passing silently through our skies. The revelation is not always comfortable. Anomalies remind us that our models are incomplete. Silence reminds us that our questions may go unanswered. The possibility of surveillance, however unlikely, reminds us that revelation can also mean exposure. But this discomfort is part of the process. The universe is not revealed to reassure us. It is revealed to confront us with reality, to force us to expand beyond the limits of our expectations. Each visitor challenges us to refine our understanding, to face uncertainty, and to live with the knowledge that we are part of something far larger than we once imagined. The future will bring more revelations. As surveys grow more powerful, the stream of detections will increase. Some will be routine, blending into catalogues with little notice. Others will stand out, demanding attention through their speed, their chemistry, or their trajectories. Each will add to the mosaic of understanding. The Vera Rubin Observatory alone is expected to discover many such objects, and with each discovery, the galaxy will come into sharper focus. Not complete focus, never complete, but clearer than before. The universe will reveal itself not in sudden clarity, but in the gradual accumulation of detail. We may one day intercept one of these visitors directly, sending a spacecraft to meet it before it escapes into the dark. If that happens, the revelation will be more profound still. Touching, sampling, studying material from another star system would be an expansion of science unlike any before. But even without such missions, the revelation continues. Spectra, trajectories, and anomalies are enough to keep building the picture. We do not need to capture the entire message at once. The universe reveals itself patiently, and patience is part of the process. This slow revelation carries a lesson about perspective. Humanity often looks for certainty, for answers that are clear and complete. The Wanderers remind us that knowledge rarely comes that way. The universe is too complex, too vast, to be explained in a single discovery. Instead, it is revealed through fragments, through ambiguity, through mysteries that linger even after years of study. This is not a flaw. It is the nature of reality. To demand more is to misunderstand the scale of what we are trying to grasp. To accept the slow revelation is to align ourselves with the universe itself, which speaks not in declarations but in wanderers. In this sense, every visitor is both ordinary and extraordinary. Ordinary because they are fragments of matter shaped by processes we understand. Extraordinary because they bridge the distance between stars, carrying with them histories we cannot otherwise access. They do not need to be probes or signals to be significant. Their very existence is revelation. They tell us that the galaxy is not distant but immediate, not silent but filled with movement, not inaccessible but passing through us constantly. The universe is revealed not through rare events, but through the steady presence of what has always been there, waiting for us to notice. The journey from Oumuamua to Borisov to Atlas is only the beginning. The list will grow, the catalogue will expand, and with it our understanding. Each name added to the record will mark another step in the unfolding of the universe. The revelation will not come as a single story. It will come as a series, each chapter written by a different fragment, each visitor carrying its own part of the message. Together they will form a narrative that is larger than any one object, larger than any one anomaly, larger than any one interpretation. The universe revealed one wanderer at a time is not the story of us discovering the galaxy. It is the story of the galaxy revealing itself to us piece by piece in ways that are undeniable and unplanned. We are not the centre of that story. We are participants in it, observers who happen to become aware at the moment when instruments grew sharp enough to notice. The galaxy has always moved through us. Now at last we can see it happening. That is the revelation. Not that we are being watched, not that we are alone or not alone, but that the universe is in motion, and in that motion it reveals itself. And so the process continues. The next detection will come, and the one after that, and the one after that still. Each will bring its own questions, its own debates, its own balance of curiosity and fear. Each will add to the mosaic, to the slow unfolding of knowledge. The universe is not silent. It speaks through wanderers, through fragments, through anomalies. It reveals itself not in grand events, but in countless small ones. And we, watching from our small planet, will continue to listen, to measure, to wonder. The revelation will not end. It will only expand, one wanderer at a time,